Hello there and welcome to Physics with William, where the universe slows down just enough for us to have a good look around before sleep. Tonight, we are turning our attention to something so familiar that it is almost easy to forget how extraordinary it is. It rises over our roofs, warms our faces, wakes the birds, fades the stars, and quietly powers almost every living thing you have ever seen. It is the reason mornings exist in the way we know them, the reason leaves unfold, winds move, clouds gather, oceans shimmer, and sleepy cats find exactly the right rectangle of warmth on the floor. Tonight, we're going to drift toward the sun. Not too quickly, of course, because that would be both uncomfortable and extremely poor planning, and ask a simple question that turns out to be enormous. What actually happens inside the sun? Before we begin, I would love to know where in the world you are listening from tonight, and whether the sun is up where you are, or whether it has already slipped below the horizon and left you in the softer company of evening. Perhaps you're hearing this while the room is dark and quiet. Perhaps there is rain against the window, or a lamp beside the bed, or maybe it is morning for you, and the real sun is already stretching across the walls. It is a nice thought, really, that all of us are living under the same star but meeting it at different angles, different hours, different moods. Somewhere, someone is watching dawn arrive. Somewhere else, someone is closing the curtains. And above all of it, steadily and without fuss, the sun continues its work. If you find this kind of gentle science soothing, or if you enjoy learning about the universe in a way that does not rush you, I would be very grateful if you gave the video a like, and perhaps subscribed if you have not already. It helps this quiet little corner of curiosity reach more people who might want a peaceful place to rest their minds. And if you do fall asleep before we get very far, that is perfectly all right. The sun will still be there in the morning, which is considerate of it, really. It has been keeping its appointments for quite a while. Now, when we look at the sun, we are looking at something that feels almost ordinary because it has always been there. It is part of the background of being alive. We do not usually wake up and think, how remarkable that an enormous glowing sphere of plasma is holding the solar system together while turning hydrogen into helium at its centre. Most of us just think, where did I leave my keys? And is there enough milk for tea? But the ordinary feeling of sunlight hides one of the most powerful physical processes in nature. The sun is not burning like a campfire. It is not a giant ball of flame in the way a candle is flame, or a log is flame, or the suspiciously overdone corner of toast is flame. Fire, as we know it on Earth, needs oxygen and fuel and a chemical reaction. The sun is doing something much deeper, much stranger, and much more efficient. It is powered by nuclear fusion, happening under pressures and temperatures so extreme that matter behaves in ways we never see in everyday life. But let us not rush straight into the centre. The sun deserves a slower approach. After all, from Earth it looks smooth and simple, a bright disk in the sky. Children draw it as a yellow circle with lines around it. Weather forecasts use a cheerful little icon. Ancient people watched it rise and set and built calendars around it. Farmers trusted it. Sailors navigated by it. Poets compared people to it. Cats, again, continued to sit in it with great seriousness. But the real sun is not a neat golden circle. It is a layered, boiling, magnetic, vibrating star, larger than we can comfortably imagine, and so active that even calling it calm feels a little unfair. It only seems calm because we are very far away, and distance has a wonderful way of making chaos look peaceful. The sun is about 150 million kilometers from Earth, though even that number can glide past the mind without leaving much of a footprint. So here is another way to think of it. Light, which moves faster than anything else in the universe, takes a little over 8 minutes to travel from the sun to us. That means when sunlight lands on your hand, or slips through your curtain, or makes a dusty room suddenly visible, it has already been travelling through space for minutes before it reaches you. But that is only the final little sprint. Before that light ever left the sun's surface, it may have spent thousands of years wandering through the inside of the star, bouncing, scattering, being absorbed and re-emitted, taking an outrageously indirect route outward. A photon born in the sun's core does not simply dash to freedom like someone late for a train. It stumbles through a crowded, glowing maze, nudged and redirected over and over again. In that sense, the sunlight you see today began its journey long before you did. Long before your morning alarm. Long before the kettle boiled. And possibly long before anyone remembered where they put the good scissors. That is one of the lovely strange things about the sun. It connects the immediate with the ancient. You feel sunlight instantly, but the energy behind it has a history. It began in the deep core where matter is squeezed so tightly and heated so fiercely that atomic nuclei can collide and join. In those collisions, tiny amounts of mass are converted into energy. It sounds small, and on the scale of individual particles it is small, but the sun is not doing this once or twice. It is doing it constantly, in numbers so large they stop behaving like numbers and start behaving like weather. Every second, the sun transforms a vast amount of hydrogen into helium, releasing energy that slowly works its way outward until it becomes the light and heat that reach Earth. Inside the sun, there is no solid ground. There is no surface you could stand on, no glowing floor, no fiery cavern with walls. The sun is made mostly of plasma, a state of matter in which atoms are stripped apart into charged particles. It is like gas, but more electric, more responsive to magnetic fields, more restless. If ordinary gas is a crowd of people wandering through a station, plasma is that same crowd during a very confusing announcement, with everyone charged up, pulled this way and that, moving in currents and swirls. The sun is plasma almost all the way through, shaped by gravity, pressure, heat, and magnetism. It is not a simple object. It is a balancing act. Gravity is always trying to pull the sun inward. Every bit of the sun attracts every other bit, and because the sun is so massive, that inward pull is immense. If gravity had its way completely, the sun would collapse under its own weight. But fusion in the core produces energy, and that energy creates outward pressure. So the sun sits in a long-lasting balance. Gravity presses inward, heat and radiation push outward. Neither side fully wins. This balance is what allows the sun to shine steadily for billions of years, rather than exploding all at once or crumpling immediately into a much denser object. It is not a quiet balance in the sense of stillness. It is more like the balance of a person riding a bicycle, constantly adjusting, constantly moving, yet stable overall. The sun is not frozen in place. It is continuously maintaining itself. And because it is maintaining itself, the sun has structure. Not structure like a building with beams and rooms, but structure made from conditions. In the core, fusion dominates. Outside the core, energy travels through a thick region where radiation passes from particle to particle. Farther out, the material becomes less dense, and giant currents of hot plasma rise and cooler plasma sinks, like a pot of soup simmering on the stove, if the soup were larger than a planet and not recommended for lunch. Near the visible surface, these currents form patterns, cells of bright rising material edged by darker sinking lanes. Above that surface, the sun's atmosphere extends outward, becoming hotter in ways that are still surprisingly difficult to explain fully. And threaded through all of this are magnetic fields, twisting and tangling until they sometimes snap into spectacular eruptions. It is tempting to think of the sun as steady because our days depend on it being steady. Sunrise, noon, sunset, summer, autumn, winter, spring. From our point of view, it behaves with admirable routine, but close up the sun is alive with motion. Its surface churns, its magnetic fields loop into space, dark sunspots appear and vanish, flares burst, great arcs of plasma rise and fall. Sometimes the sun throws charged particles outward in enormous storms that can race across the solar system. When those particles reach Earth, our planet's magnetic field catches much of the impact, and near the poles the atmosphere lights up in curtains of aurora. So even the northern lights, those slow green and red shimmers across polar skies, are part of the sun's story. They are sunlight's more dramatic cousin, the kind that arrives wearing a cape and asking everyone to look outside. All of this is happening not in some distant, exotic corner of the universe, but in our own neighbourhood. The sun is our nearest star. That phrase can sound almost too casual. Nearest star, nearest. Like nearest post office, nearest bakery, nearest place that always seems to be closed when you finally get there. But the sun is a star, and that matters. It is not a special category of object separate from the stars we see at night. It is one of them, only much closer. Every star in the night sky is a sun in the broad sense, though many are larger, smaller, hotter, cooler, younger, older, quieter, or far more temperamental. The only reason our sun does not look like a tiny point is that we live beside it. We are not watching it from across the galaxy. We are orbiting it, warmed by it, held by its gravity, and protected in some ways by the steady energy it provides. That closeness has shaped human life completely. Our bodies respond to sunlight. Our sleep cycles lean on it. Plants use it to build sugars from air and water, and nearly every food chain on Earth begins there. Coal, oil, and gas are ancient sunlight stored in biological matter and buried over millions of years. Wind patterns are driven by uneven heating from the sun. The water cycle, with evaporation and clouds and rain, depends on solar energy. Even the weather you complain about politely or not so politely is part of the sun's influence. A cloudy afternoon, a summer drought, a sea breeze, a thunderstorm rolling over hills, all of it connects back to our star-warming Earth unevenly and setting the atmosphere in motion. And yet, the sun is not simply a background provider of daylight. It is a physical system with a past and a future. It was born about 4.5 billion years ago from a collapsing cloud of gas and dust. Most of that material gathered into the young sun, while the leftover disk around it eventually formed planets, moons, asteroids, and all the other bits and pieces of the solar system, including the particular rocky world where you and I now discuss stellar interiors in a soothing voice. The sun has been shining for billions of years, and it will continue to shine for billions more. It is currently in the long, stable middle period of its life, fusing hydrogen in its core. It is not young, but it is not old in a dramatic sense either. It is middle-aged, which perhaps explains why it is reliable, powerful, and occasionally produces magnetic outbursts. The question of what happens inside the sun is also a question of how stars make the universe workable. Stars are not just pretty lights, they are engines of transformation. In their cores, light elements become heavier elements. In the lives and deaths of stars, the raw materials for planets and living things are made and scattered. The calcium in bones, the iron in blood, the oxygen you breathe, the carbon in every cell of your body, these elements have histories tied to stars. Our own sun is not massive enough to make all of them, and it will not end its life in the most violent kind of stellar explosion, but it belongs to the same great family of processes. When we study the sun, we are studying the nearest example of a star at work. It is the one star close enough for us to see in detail, measure carefully, and complain about when it gets in our eyes while driving. There is something grounding about that. The sun is enormous beyond daily experience, but it is also intimate. You know it by warmth on your skin. You know it by shadows on the pavement. You know it by the way a room changes when a cloud passes over. You do not need a telescope to know the sun matters. But science lets us go further than instinct. It lets us ask what kind of object can shine for billions of years without running out quickly. It lets us ask why the sun has layers, why its surface looks grainy, why its atmosphere is strangely hot, why magnetic storms happen, why sunlight takes so long to escape, and why the whole thing does not simply fly apart or fall inward. Science takes the familiar and gently removes the wrapper. For a long time, people did not know how the sun worked. That is worth remembering. It may seem obvious now to say nuclear fusion powers the sun, but for much of human history, the sun's source of energy was a genuine mystery. Chemical burning could not last long enough. Gravitational contraction could provide energy, but not enough for the age of Earth that geology and biology began to reveal. The deeper answer required knowledge of atoms, nuclei, mass, energy, and the strange rules of the very small. Only when physics learned to look inside matter could it understand the light in the sky. The sun forced science to grow up in a way. It sat there shining, calmly contradicting any explanation that was too small. This is one reason the sun is such a beautiful subject for a sleepy science journey. It is familiar enough to feel comforting, but deep enough to lead us into nearly every major idea in physics. Gravity, pressure, heat, light, magnetism, plasma, particles, waves, radiation, time, and the life cycle of stars are all involved. The sun is not just one lesson. It is a whole library glowing at the centre of our solar system, and like any good library, it is best entered slowly, with a little respect and perhaps a warm drink nearby. So tonight, we will not treat the sun as a simple golden disk or a burning ball in the sky. We will imagine moving inward carefully, layer by layer, asking what each region does and how energy makes its way from the crushed core to the light that reaches Earth. We will picture the core where fusion begins, the crowded interior where photons wander for ages, the convective regions where plasma rises and falls, the visible surface that shines into space, and the magnetic storms that remind us our star is not merely bright but active. We will keep the pace gentle, because the sun has been doing this for billions of years and is not in a hurry, even if we occasionally are. And perhaps, as we move closer in thought, the sun will become a little less like a flat circle in the sky, and a little more like what it really is. A star. A vast sphere of plasma held together by gravity, powered by fusion, layered by pressure and heat, restless with magnetism, and generous enough to send energy into space in every direction, including the tiny portion that lands here and makes Earth glow with life. Not generous on purpose, of course. The sun is not deciding to warm the garden or help the laundry dry. It is simply obeying physics with magnificent consistency. Still, from down here, it feels almost kind. To understand what actually happens inside it, the first thing we need to do is let go of the most common picture. The sun is not a bonfire. It is not a furnace full of ordinary flames. It is something stranger and far more stable. A star whose light begins far below the surface, in a place where matter is squeezed, heated, and transformed. And before we can follow that light from the centre outward, it helps to ask what kind of thing the sun really is, and why calling it a fireball misses nearly everything important. The easiest mistake to make with the sun is also the most natural one. We look up, we see something bright and hot, and the mind reaches for the nearest familiar idea. Fire. It is glowing. It gives off heat, it lights the world, and it is not something you would wisely try to touch. So for everyday language, calling the sun a ball of fire seems reasonable enough. It gives the right feeling. In the same way, calling a whale a very large fish gives the right feeling until a biologist gently clears their throat from across the room. The sun is not fire. It is not burning in the ordinary sense. It is not a cosmic bonfire. Not a lump of coal in the sky, not a furnace stuffed with fuel and oxygen. It is a star, and that one word carries a whole different kind of physics inside it. Fire on Earth is chemical. When a candle burns, wax reacts with oxygen in the air. When wood burns in a fireplace, molecules in the wood break apart and recombine with oxygen, releasing heat and light. It is a rearrangement of electrons and chemical bonds. Very useful, very cosy, and excellent for marshmallows if handled responsibly. But chemical burning is not powerful enough to explain the sun. If the sun were made of coal or wood or oil, it would not shine for billions of years. It would burn through its available fuel far too quickly. The fact that the sun has been shining over Earth for the entire history of life tells us that something deeper must be happening, something more efficient than chemistry, something rooted not in the outer parts of atoms but in their centres. That deeper process is nuclear fusion. In the sun, the important action happens in the atomic nuclei, the tiny dense centres of atoms. Under the immense pressure and temperature in the core, hydrogen nuclei can be forced close enough together to join and eventually form helium. That joining releases energy. It is not the sort of burning that needs air. It is not fed by oxygen. It would not go out in space. In fact, space is exactly where stars belong. The sun shines because its own gravity has squeezed its central regions until matter reaches conditions extreme enough for fusion to occur. It is not being burned from the outside, it is being powered from within. This is a useful distinction because it changes how we imagine the whole object. A fire consumes material where it meets oxygen. Flames flicker at edges. A log burns from its surface inward. A candle flame dances because hot gases rise and cooler air moves in. But the sun is not a flame licking around a solid body. There is no wooden centre being eaten away. There is no glowing crust with fire on top. The sun is mostly plasma, a hot electrically charged state of matter, and it is held together by gravity. Its light begins deep inside, where the pressure is highest, and then works outward through layer after layer before it escapes into space. So when we see the sun shining, we are not seeing combustion. We are seeing the surface release energy that began its journey in the core long ago. It can be slightly surprising to hear that the sun has no solid surface. From Earth it looks like it does. It appears to have a sharp edge, a round boundary, a visible face. But that edge is only where the gas becomes thin enough for light to escape freely into space. If you could approach it, which would be brave in the least sensible way, you would not find a hard shell. You would pass into hotter and denser plasma. The visible surface is called the photosphere, and it behaves like the place from which sunlight finally streams outward, but it is not a floor. It is more like the glowing top of an enormous atmosphere, a layer where the sun changes from opaque to transparent. Saying the sun has a surface is useful, but only if we remember that stars use the word surface in a very relaxed way. This is part of what makes stars strange compared with familiar objects. A planet like Earth has a surface because gravity has pulled heavy material into a solid or liquid body with a boundary you can stand on, at least in some places, preferably not in the ocean without a boat. The sun is different because it is so hot that ordinary atoms cannot remain ordinary in much of it. Electrons are stripped away from nuclei and the result is plasma. Plasma is often called the fourth state of matter, after solid, liquid and gas, though it is not rare in the universe at all. In fact, most of the ordinary matter we can see across the cosmos is plasma, because stars are made of it. We are the unusual ones, living on a cool rocky world where matter can settle into chairs, teacups, bookshelves and biscuits. Plasma behaves in ways ordinary gas does not. Because it contains charged particles, it responds strongly to magnetic fields. This is one reason the sun has such a restless personality. Magnetic fields inside and around it can twist, stretch, loop, and snap into new arrangements. They help produce sunspots, flares, and eruptions. A campfire may crackle and spit, and occasionally send a worrying spark onto the carpet, but it does not have planet-sized magnetic storms. The sun does. Its star nature is not just about fusion in the core. It is also about being a giant self-gravitating plasmasphere, with energy flowing through it and magnetic fields threading it like invisible elastic cords. The sun is also not yellow in the simple way many drawings make it appear. From space, without Earth's atmosphere scattering light around, the sun looks close to white because it emits light across many visible colours at once. From the ground, it often appears yellow, orange or red because our atmosphere scatters shorter wavelengths more strongly, especially when the sun is low in the sky and its light passes through more air. This is why sunsets can look so warm and dramatic, as if the sky has decided to make a strong artistic choice before bedtime. But the sun itself is not a neat yellow object. It is a glowing star whose colour tells us about its surface temperature. Hotter stars can look blue-white. Cooler stars can look orange or red. The sun sits in a middle range, not the hottest kind of star, not the coolest, but very comfortably important to us. Calling the sun a star also means placing it among other stars. It is not the largest star, nor the smallest, nor the brightest in the galaxy. It is fairly ordinary in many ways, which is one of its charms. There are stars so huge that if placed where our sun is, their outer layers would reach far beyond the orbit of the inner planets. There are stars much smaller and dimmer, glowing red for astonishing stretches of time. There are stars that live fast and die violently, and stars that last so long the universe itself has not yet been around long enough to see them fade. Our sun belongs to a stable middle category, massive enough to fuse hydrogen steadily in its core, but not so massive that it burns through its fuel in a short dramatic life. It is the sort of star that gives a planet time. Time for oceans, time for rocks to weather, time for chemistry to become biology, time for life to become complicated enough to wonder what the sun is doing. That ordinariness is scientifically valuable. Because the sun is near, we can study it in far more detail than any other star. Other stars are often just points of light, even through powerful telescopes. We can measure their brightness, colours, motions and spectra, and from those clues learn impressive amounts about them. But the sun shows us a star as an actual object, with visible surface patterns, eruptions, vibrations and changing magnetic behaviour. It is our local laboratory for stellar physics. When scientists study the sun, they are not only learning about our own daylight, they are learning how stars work across the universe. For a long time, the idea that the sun was just another star was not obvious. The sun dominates the day. The stars appear only as faint points at night. They seem like different categories of things. The sun feels close, warm, and commanding, while the stars feel distant and decorative, as if someone scattered pinholes through the darkness. But astronomy gradually revealed that the difference is mostly distance. The stars are suns, and the sun is a star. This is one of those ideas that sounds simple once you accept it, but it rearranges the imagination. The bright disk that warms your face and the tiny lights overhead belong to the same family. Day and night are not separate worlds. They are different views of the same universe. Understanding the sun as a star also helps explain why it is round. It is not round because it was made that way by some surface process, like a soap bubble floating in air. It is round because gravity pulls inward from every direction. When an object has enough mass, gravity smooths it into a sphere. Mountains and rigid structures can resist this on smaller worlds. But in a hot plasma body like the sun, material flows and adjusts. The result is a nearly spherical star, slightly flattened by rotation, but close enough to round that it looks perfectly circular to us. The sun's roundness is gravity made visible. Gravity also explains why the sun does not simply drift apart. The particles inside it are extremely hot and moving rapidly. Heat creates pressure. Pressure pushes outward. If pressure were the only thing that mattered, the sun would expand. But gravity pulls inward, trying to compress all that material. The sun exists in a balance between those two tendencies. This balance is not a frozen piece. It is a dynamic balance, maintained moment by moment. Fusion in the core keeps the interior hot enough to provide outward pressure. Gravity keeps the whole star confined. If the core produced less energy for a while, gravity would squeeze it tighter, which would tend to raise the temperature and encourage more fusion. If the core produced more energy, the sun would expand slightly, reducing central conditions and easing the fusion rate. In this way, the sun regulates itself naturally, not with intention of course, but through physics. It is like a thermostat made of gravity and plasma, which is impressive, though difficult to install in a hallway. This self-regulation is one of the reasons the sun can shine so steadily. We often think of power as noisy or explosive. Engines rattle, fires roar, lightning cracks. But the sun's output, although enormous, is stable over human lifetimes. There are changes and they matter. The sun has cycles of magnetic activity. Its surface features come and go. It produces flares and storms. But its overall light output changes only slightly from year to year. That steadiness has been essential for Earth. Life can adapt to seasons and weather, but it would have a much harder time with a star that randomly doubled in brightness before lunch and then sulked in the afternoon. The sun is active, but it is not wildly unstable. It is a star in a long balanced phase. If we compare it to a fire, fire consumes fuel in a way that is easy to see. A candle grows shorter, logs become ash, smoke rises, there are leftovers, and the process feels local and temporary. The sun's fuel is hydrogen in its core, but it's not disappearing in the same way a log disappears. It is being transformed into helium, with a small portion of mass becoming energy. That energy becomes light, heat, and moving particles. The sun is slowly changing its inner composition. Over billions of years, helium builds up in the core while hydrogen is used. These changes are gradual, but they are real. The sun is stable, not permanent. It is not a machine that can run forever. It has a life story, and we are living during its calm middle pages. The scale of the sun's energy can feel impossible to grasp. Every second it releases more energy than humanity has used in all of recorded history, by a margin that is not worth trying to fit into a tidy comparison. And yet, Earth intercepts only a tiny fraction of that energy. Most sunlight flies away into space, travelling outward in all directions. The portion that reaches Earth is enough to drive climate, weather, photosynthesis, and nearly all surface life. That is both humbling and slightly funny. Our entire biosphere runs on a small spill of energy from a star that is not aiming at us. We are warmed by the leftovers of a process far larger than our planet. This leads to another helpful point. The sun does not shine because it is trying to light Earth. It would shine even if Earth did not exist. It was already shining before people, before trees, before animals, before the first cells in ancient oceans. It shines because gravity and fusion make it shine. The fact that Earth sits at a distance where some of that energy can support liquid water, and life is a result of planetary formation and orbital arrangement, not solar kindness. Still, it is hard not to feel some affection for it. We evolved under this star. Our eyes are tuned to the light it sends, our skin responds to it, our clocks and calendars are built around its apparent motion, even our moods can lean toward it. The sun may not care, but we do, and perhaps that is enough. The difference between a star and a fire also matters when we think about space. A flame in a vacuum goes out because chemical fire needs oxygen and gas flow. The sun sits in space, surrounded by near vacuum, and continues without difficulty because its fuel and its reaction are internal. It does not need air. It does not need a draft. It does not need someone to poke it with a metal stick while making thoughtful fireplace noises. The sun carries its own conditions within itself. Gravity creates pressure. Pressure and temperature enable fusion. Fusion produces energy. Energy moves outward. That is the chain. No oxygen required. This does not mean oxygen is absent from the sun. The sun contains many elements in small amounts besides hydrogen and helium, including oxygen, carbon, nitrogen, iron, and others. Astronomers often refer to these heavier elements in a broad way, even though many of them are not metals in everyday speech. But hydrogen and helium dominate. The heavier elements are like seasoning in an enormous soup, important for details but not the main ingredient. The sun's composition reflects the material from which it formed, a cloud already enriched by earlier generations of stars. In that sense, even our sun was not the beginning of the story. It was born from gas and dust that had been shaped by stars before it. A star begins when a region of a cold cloud in space collapses under gravity. As material falls inward, it heats up. The center becomes denser and hotter. At first, the forming star shines because of gravitational energy, the energy released as material contracts. But once the core becomes hot and dense enough, fusion begins. That is the moment the object becomes a true main sequence star, steadily fusing hydrogen into helium in its core. The Sun entered that phase billions of years ago and remains there now. Main sequence sounds a little like an administrative category, perhaps something on a school form, but it is one of the most important ideas in astronomy. It describes the long, stable phase when a star shines by hydrogen fusion in its core. Our Sun is in that phase, and that is why it has been such a dependable companion for Earth. The word star can sometimes make the Sun feel more distant, more astronomical, less personal. But it should do the opposite. It should make the stars feel closer. Every point of starlight at night is a physical object, not a decoration. Some may have planets, some may be surrounded by dust, some may be young and wild, some may be old and swelling toward the next stage of life. Our Sun is the one example we can study intimately, and by understanding it, we gain a key to the others. It is like having one tree in your garden and realizing that forests everywhere obey related patterns of roots, leaves, water, and light. The details vary, but the underlying nature connects them. The Sun's star nature also explains why it can affect Earth beyond visible light. It emits ultraviolet radiation, which interacts with our atmosphere and can damage living tissue if not filtered and moderated. It emits streams of charged particles called the solar wind, which flow outward through the solar system. It creates magnetic storms that can disturb satellites, communications and power systems. A campfire warms the people sitting near it. A star shapes space around it. The Sun fills the solar system with its influence, carving out a vast bubble in the surrounding interstellar environment. Earth moves inside that bubble, protected by its own magnetic field and atmosphere, but never completely separate from solar activity. Even the quiet Sun is not truly quiet. Its surface is constantly moving. Hot plasma rises, cools, and sinks. Waves travel through it. Magnetic regions emerge and decay. If we could hear the Sun directly, not through space because sound does not travel through vacuum, but by translating its vibrations into sound, it would be full of low resonances, a vast ringing sphere. Scientists study those vibrations to learn about the interior, a technique rather like using the ringing of a bell to infer what the bell is made of. The Sun trembles with information. It is not a solid lamp in the sky. It is a resonating, churning, magnetized star. This brings us back to the importance of letting go of fire as the main image. Fire is too small, too surface-based, too temporary. The Sun is not a thing being consumed by flames. It is a self-gravitating nuclear engine, a plasma sphere in long-term balance, transforming matter in its core and sending energy outward through a layered interior. It shines because the universe permits matter, under the right conditions, to release deep stores of energy. It shines because gravity compresses. It shines because nuclei fuse. It shines because pressure, heat, radiation, and magnetism interact across scales from tiny particles to the entire solar system. And yet, even after all that, the everyday Sun remains the one we know. The light on the kitchen table, the warmth on a winter morning, the glare that makes you search for sunglasses you definitely left somewhere sensible. Science does not take that away. It adds depth to it. When you stand in sunlight, you are feeling the outer expression of processes that began in a core you will never see directly, inside a star that is ordinary by cosmic standards and completely extraordinary by human ones. You're being touched by energy born from fusion, delayed by a long interior journey, released from a glowing surface, and carried through space to Earth. Not firelight, starlight. The next step is to move inward from that visible face and ask where the light really begins. Not at the surface we see, not in the bright layer that shines into space, but deep below it, in the dense central region where the sun's gravity has done its most intense work. Down there, in conditions beyond anything on Earth, the sun's long, steady brightness is made particle by particle, collision by collision, in the hidden core where the star quietly earns its name. To reach the place where the sun earns its name, we have to imagine sinking far beneath the bright surface we see from Earth. Not falling through empty space, not drifting through a clear glowing atmosphere, but moving inward through plasma that becomes hotter, denser, and more tightly packed with every step of the journey. The sun may look smooth from a distance, almost like a calm, round lamp in the sky, but inside it is a world of pressure. Gravity has gathered an enormous amount of material and pressed it inward for billions of years, and the deepest part of that pressure is found in the core. This is where the sun's light begins, not as the soft golden sunlight that reaches your window, and not as the warm patch on the carpet where a cat has made a very wise decision, but as raw energy born in a place so extreme that ordinary comparisons start to feel a little embarrassed. The core is the central region of the sun, the innermost heart of the star. It is not large compared with the whole sun, but it is by far the most important region for the sun's power. Most of the sun's energy is made there, in the dense central furnace, where gravity has squeezed matter into conditions that allow nuclear reactions to happen. Even calling it a furnace is not quite right, because furnaces are machines we build, and this is not a machine in any human sense. It has no walls, no switches, no carefully labelled panel that says please do not touch. It is simply matter under such intense pressure and heat that it begins to transform itself. The core is where hydrogen becomes helium, where a tiny loss of mass becomes a great release of energy, and where the long story of sunlight begins. If you could somehow place yourself in the sun's core, which would be a heroic failure of travel planning, you would not see anything like a landscape. There would be no horizon, no glowing floor, no ceiling of flame. There would be no orange tongues of fire curling upward, no sparks, no smoke, and certainly nowhere sensible to sit. The core is plasma, an intensely hot state of matter in which atoms are no longer neat little systems, with electrons calmly orbiting around them. The particles are stripped apart, crowded together, and moving with enormous energy. The environment is so dense that light cannot travel freely. A photon cannot simply set off in a straight line and escape. It is surrounded at every moment, jostled by charged particles, absorbed, re-emitted, redirected and delayed. The core is brilliant, but it is not transparent. It is full of trapped energy trying very slowly to work its way outward. The numbers that describe the core are difficult to feel in a human way. The temperature is in the millions of degrees. The pressure is beyond anything we experience on Earth. The density is far greater than the air around you, and far greater than water, even though the sun is made mostly of hydrogen and helium, elements we often think of as light. This is one of those cases where gravity changes the meaning of lightness. A single hydrogen atom is light, yes, but gather enough hydrogen into a star and gravity squeezes it into something entirely different. The core is dense because the weight of the entire sun above it presses down. Every layer pulls inward. Every particle is part of a vast gravitational crowd. At the centre, there is nowhere farther inward for the pressure to go, so it builds into the conditions that make fusion possible. This pressure is not a detail. It is the reason the sun works. Hydrogen nuclei, which are positively charged, normally repel each other. They do not naturally want to merge. In everyday conditions, they would avoid one another like polite strangers at a crowded party, who both reached for the same biscuit and decided it was not worth the awkwardness. But in the core, the temperature is so high that the particles move extremely fast, and the pressure is so great that collisions are unavoidable. Every so often, under the right conditions, hydrogen nuclei get close enough for the forces inside atomic nuclei to take over. When that happens, the particles can join in a chain of reactions that ultimately produces helium and releases energy. This is why the core is not merely hot, it is productive. Heat alone is not enough to make a star shine for billions of years. Pressure alone is not enough either. The core works because it has both in the right combination, maintained by the sun's own mass. Gravity squeezes the core heats, fusion releases energy, and that energy helps support the sun against further collapse. It is a balancing act that has been going on since the sun settled into its long, stable life. The sun does not need to be held up by anything solid. It is held up by pressure, and that pressure is fed by the energy born at the centre. There is something quietly elegant about that. Gravity tries to crush the sun inward, and in doing so, it creates the very conditions that allow the sun to push back. It is almost as if the sun's problem becomes its solution. The more gravity presses the core, the more capable the core becomes of producing energy. But this does not run away endlessly, because stars like the sun are self-regulating. If fusion in the core were to slow, the core would contract slightly under gravity, becoming hotter and denser, which would encourage fusion again. If fusion became a little too energetic, the core would expand slightly, cooling and easing the reaction rate. The sun is not consciously adjusting itself, of course. It is not sitting there with a clipboard, checking central temperature and muttering about maintenance schedules. It is simply following physics, but the result is remarkably stable. This stability is why life on Earth has had time to develop. The sun's core does not produce energy in wild bursts from one century to the next. It has variations, and the outer layers can be very active, but the deep engine is steady on human timescales. It is not like a fire that flares when you add fuel and fades when the wood is gone. The core contains a vast reservoir of hydrogen, and the fusion process proceeds gradually. Slowly, over billions of years, hydrogen in the central region is being converted into helium. The sun is changing, but it is changing with the patience of geology and astronomy, not with the impatience of a candle flame. Still, the core is not static. It is not a quiet, glowing marble at the centre of the sun. Particles are constantly moving, colliding, scattering and reacting. Energy is being produced in many small events, each one tiny on its own, but together powerful enough to make the star shine. It is a little like listening to rain. One drop is small, 1,000 drops make a sound. A storm becomes an atmosphere. In the sun's core, individual nuclear events happen across an enormous volume of dense plasma, and together they create the total energy output of the star. The light that falls on Earth begins in countless microscopic interactions, none of them impressive by themselves in a human sense, but collectively responsible for daylight, weather, plants, and the habit of squinting when someone opens the curtains too quickly. The energy born in the core first appears in forms far more intense than ordinary sunlight. It is not produced as the comfortable visible light that your eyes can see. Much of it begins as high-energy radiation, along with fast-moving particles. Over time, as this energy is absorbed and re-emitted throughout the sun's interior, it is transformed, softened, redistributed. By the time it finally emerges from the surface, it has become the broad mixture of light we know as sunlight. This means the sunlight on your skin has been through a long history of transformation. It was born in the core under extreme conditions, then shuffled outward through layer after layer, losing its original identity many times over. By the time it reaches Earth, it is no longer a simple messenger from a single event. It is the final result of a long, crowded journey through a star. One of the most fascinating things made in the core is not light in the usual sense, but neutrinos. These are tiny particles produced in nuclear reactions, and unlike photons, they barely interact with matter. While light is trapped inside the sun for a very long time, neutrinos escape almost immediately. They stream out from the core, pass through the rest of the sun, cross space, pass through Earth, and continue onward as if planets are no more troublesome than a faint mist. Every second, enormous numbers of solar neutrinos pass through your body. You do not feel them. They do not warm you. They do not announce themselves. They simply pass through, carrying direct information from the sun's core. If photons are slow travellers that get delayed in the crowd, neutrinos are the quiet guests who leave through the side door before anyone notices. For scientists, neutrinos are precious because they come almost straight from the core. We cannot see into the sun with ordinary light because the interior is opaque. The sunlight that reaches us comes from the visible surface, not directly from the centre, but neutrinos give us evidence of what is happening deep inside. They confirm that nuclear fusion is taking place there. They are like whispers from the heart of the sun, so faint that detecting them requires enormous and sensitive instruments, often placed deep underground to shield them from other noise. It is rather charming in a scientific way that to listen to the centre of the sun we build detectors in darkness beneath Earth. The lightest messengers from the brightest object in our sky are caught in quiet underground places. The core also reveals why the sun is not simply hot all the way through in the same way. Temperature changes with depth. The surface is hot enough to glow, but the core is far hotter. This may feel counterintuitive because the surface is what we see, and what we see looks intensely bright. But stars are not heated from the outside inward. They are powered from the inside outward. The surface shines because energy has reached it, not because that is where the main energy is made. The core is the origin. The outer layers are the path. The surface is the release. It helps to imagine the sun as a long conversation between gravity and energy. Gravity speaks first, pulling gas inward during the sun's formation, compressing the central region until fusion begins. Once fusion starts, energy answers back. It pushes outward through pressure and radiation. The core is where that answer is strongest, where the sun resists collapse from within. Without the core's energy production, the sun could not remain the size and brightness it is now. It would contract, heating as it shrank, until some new balance or new state emerged. But because fusion continues, the sun holds itself open. It is a star because its core can push back against its own gravity. This does not mean every part of the sun is producing energy equally. The core does most of the work because only there are the conditions extreme enough for hydrogen fusion to proceed at the needed rate. Move outward from the centre, and the temperature and pressure drop. Fusion becomes much less common and then effectively stops. The outer layers are not separate from the core, of course. They are part of the same star, but they are not the main power source. They transport, store, circulate, and eventually release energy. The core makes the light, but the whole sun participates in delivering it. The core's size compared with the sun as a whole is also worth lingering over. It occupies only the central portion, yet it powers everything we see. This is not unusual in stars like the sun. A relatively small inner region can dominate energy production because fusion is so sensitive to conditions. Slight differences in temperature and pressure can make enormous differences in how often reactions occur. So the sun is not like a lamp glowing evenly throughout. It is more like a giant body with a central engine, surrounded by layers that handle the difficult task of moving energy outward. Although difficult is a polite word. The journey outward is slow, tangled, and full of interruptions. At the centre itself, the sun's material is under the greatest compression. There, helium is gradually accumulating as hydrogen is used. Over time, this changes the core's structure. Helium is heavier than hydrogen, and as it builds up, the core slowly evolves. The sun responds to these internal changes over immense spans of time. It becomes very gradually brighter as it ages, because the changing core conditions alter the balance of fusion and pressure. These changes are slow enough that they do not trouble a human lifetime, but they matter across the history of planets. The sun we see today is not exactly the sun that shone over early Earth, and it will not be exactly the sun that shines billions of years from now. This slow evolution reminds us that the core is not only the birthplace of light, but also the keeper of the sun's future. What happens there determines how the sun will age. As hydrogen in the core is consumed, the balance of the star changes. Eventually, far in the future, the sun will no longer be able to maintain its current stable state in the same way. It will leave this long middle phase and swell into something very different. But for now, the core is still rich enough in hydrogen to continue its steady work. It is not close to running out on any human timescale. The sun is middle-aged, but in stellar terms that still leaves a very long afternoon. The core is hidden, but its effects are everywhere. Every green leaf is using energy that began there. Every breeze driven by solar heating. Every ocean current shaped partly by warmth. Every cloud lifted by evaporation. Every meal grown from photosynthesis. All of it reaches back to the central region of the sun. The core is not visible, but it is woven into daily life. When morning enters a room, the core is there in a roundabout way. When a field ripens under summer light, the core is there. When solar panels collect sunlight on a rooftop, they are harvesting energy that began as nuclear transformation in the sun's center long before it arrived as useful electricity. The core may be hidden beneath hundreds of thousands of kilometers of plasma, but it is not remote from us in consequence. There is also a gentleness in realizing that the sun's light is delayed. The energy born in the core does not rush straight out. It takes a long, wandering path, passing through regions where matter is dense enough to trap radiation again and again. The photons that finally escape are not the same in any simple way as the ones first produced. They have been absorbed and recreated many times. The sun is not a transparent lantern with a bulb at the center. It is more like an enormous glowing crowd, where energy is passed from particle to particle until it eventually reaches the outer layers. That slow passage helps smooth out changes. It means the surface does not instantly reflect every tiny fluctuation in the core. The sun's interior acts as a great buffer, turning countless nuclear events into a steady outward glow. If the core's energy could suddenly stop, the surface would not know immediately. The outer layers contain so much stored energy, and the transport of radiation is so slow that the visible sun would continue shining for a long while before the change became apparent at the surface. This is another reminder that stars do not behave like simple lamps. You cannot flip the core off and expect the surface to go dark at once. The sun is vast, layered, and slow to communicate with itself in certain ways. Its light is immediate to us once it leaves the surface, reaching Earth in minutes. But the internal story behind that light is ancient and delayed. At the same time, gravity communicates the overall balance of the star through pressure and structure. The core is not isolated from the rest of the sun. Its conditions support the layers above. The weight of those layers shapes the core. The sun is a single connected body, even though different regions behave differently. The core is the heart, but a heart does not exist apart from the body. It works because the whole structure holds it in the right state. Remove the outer mass and the pressure would change the core and the whole star would respond. Stellar interiors are conversations between layers, not separate rooms. When we say light is born in the core, we are using light in a broad and slightly forgiving way. The visible light we know is not born there fully formed. What is born there is energy. Some of it takes the form of high-energy radiation. Some of it goes into particles. Some is carried away by neutrinos. Through the sun's interior, energy changes form many times before becoming the sunlight that reaches us. So the core is not producing a neat little sunbeam that travels outward with a suitcase and a clear itinerary. It is producing energy in its most intense early form, and the star gradually turns that energy into the light we live by. The sun is both generator and transformer. This slow transformation gives the sun a kind of depth that our eyes cannot capture. We see the surface because that is where light finally escapes, but the real cause of the brightness is buried far below. This is true of many things in nature. The visible is often the final result, not the origin. A tree's leaves show the work of roots. A river's surface hides currents below. A person's calm expression may conceal an entire weather system of thoughts about whether the oven was left on. In the sun, the visible disk is the last page of a long internal process. To understand the glow, we have to read backward into the core. The core also teaches us something about scale. On Earth, we usually separate tiny things and huge things in our minds. Atomic nuclei belong to the world of the very small. Stars belong to the world of the very large. But in the sun, the two are inseparable. The behavior of tiny particles determines the light of a star larger than anything in ordinary experience. Nuclear events in the core shape the climate of planets. The very small powers the very large. This is one of the reasons physics can feel so satisfying. It finds connections across scales that seem, at first, completely unrelated. So the core is not just a hot center, it is the reason the sun shines, the place where gravity creates the conditions for fusion, the hidden source behind daylight, and the beginning of a journey that ends as warmth on Earth. It is a crowded, dense, blindingly energetic region where matter is under extraordinary pressure, yet where the overall result is a calm and steady star. The sun does not roar in the way a fire roars, it persists. It does not burn from the outside, it transforms from within. And in that central transformation, the story of sunlight begins. To understand that transformation more clearly, we need to look at what fusion actually does, not as a formula, not as a cold diagram, but as a physical process happening among particles in the deepest part of the sun. Hydrogen, the simplest and most abundant element in the star, is being pressed into a new form. Helium is slowly building. Energy is being released because the final arrangement of matter is slightly different from the beginning. The core is where the light is born, but fusion is the act of birth itself, the quiet engine behind the steady star, and the next step is to follow that engine as carefully as we can without waking the universe too suddenly. At the heart of the sun, the main event is not a roar, not a flame, not a crackling blaze, but a patient sequence of tiny collisions. It is easy to imagine something as powerful as the sun needing a dramatic engine, something thunderous and violent, perhaps a kind of cosmic blast furnace with explosions stacked inside explosions. But the real process is stranger than that, and in some ways, quieter. Nuclear fusion in the sun is not quiet because it is weak. It is quiet because it is steady. It happens in countless small steps, distributed across the dense core, each one governed by the rules of particles and forces, each one releasing a little energy, and together they make the daylight that reaches Earth. The sun does not shine because one enormous explosion is happening in its center. It shines because an immense number of tiny nuclear changes are happening all the time, in a balance so stable that it can continue for billions of years. The fuel for this engine is hydrogen, the simplest element in the universe. A hydrogen atom usually has one proton at its center, and in the sun's core, where atoms are stripped apart by heat, these protons move freely in the plasma. They're not drifting lazily. They're moving rapidly, crowded together by pressure, thrown into one another by temperature, and constantly pushed into near encounters. But there is a problem. Protons carry the same kind of electric charge, and particles with the same charge repel each other. They do not want to touch. They push apart as they approach, like two people trying to bring the same ends of two magnets together and then pretending they meant to do that. For fusion to happen, protons must get extremely close enough for the strong nuclear force to bind them together. That force is powerful, but it works only over incredibly tiny distances, so the particles have to overcome their electric resistance first. In ordinary conditions, they almost never could. If you had a jar of hydrogen gas on Earth, it would not suddenly begin fusing into helium, which is good news for jars and for anyone standing nearby. The sun's core is different because temperature gives particles speed and pressure keeps them crowded. Even then, fusion is not easy. Most close encounters fail. Protons approach, repel, and fly apart again. Over and over, the plasma tries and fails. This is actually important. If fusion were too easy, the sun would burn through its fuel far too quickly. A star like the sun shines for so long, partly because the first step in its fusion process is slow and difficult. The sun is powerful not because each particle fuses easily, but because the core contains so many particles that even rare successful events add up to an enormous total. There is also a wonderfully strange quantum detail involved. In the classical picture, many protons do not have enough energy to push through the electric barrier between them. But quantum mechanics allows a small chance that particles can tunnel through barriers they could not overcome in the ordinary way. This is called quantum tunneling, and it is one of those ideas that sounds as if the universe has quietly misplaced its own rules and decided not to mention it. The particles do not climb over the barrier in the usual sense. Instead, because they behave according to quantum probabilities, there is a chance they can appear on the other side of it. In the sun's core, this tiny chance matters enormously. Without quantum tunneling, the sun would have a much harder time shining as it does. Every warm morning, every sunlit window, every lazy patch of light on a bedspread owes something to a quantum trick happening deep inside a star. The main fusion pathway in the sun is often called the proton-proton chain, because it begins with protons and proceeds through several linked steps. We do not need equations to understand the basic story. Hydrogen nuclei combine through a sequence of transformations, eventually producing helium. Along the way, energy is released in several forms. Some leaves as radiation, some appears as the motion of particles, some is carried away by neutrinos, those ghostly messengers that escape almost immediately from the core. The finished helium nucleus is slightly less massive than the separate ingredients that led to it. That missing bit of mass has become energy. It is a tiny amount in each reaction. But in a star, tiny repeated enough times becomes world-changing. This can feel almost unbelievable. How can such a small difference in mass produce so much energy? The answer lies in the deep relationship between mass and energy. Matter is not just stuff sitting there. It is, in a very real sense, a concentrated form of energy. When nuclear reactions rearrange particles into a more tightly bound state, a small amount of mass can be released as energy. Chemical reactions, like burning wood, involve the outer electron structures of atoms and release comparatively modest amounts of energy. Nuclear reactions involve the nuclei themselves, where the energies are much greater. That is why fusion can power a star for billions of years, while chemical burning could not come close. The sun's engine works at the nuclear level, where matter's hidden energy becomes available. The word engine is useful, though slightly misleading if we imagine gears and pistons. The sun has no machinery in the human sense. Fusion is the engine because it is the process that supplies the energy needed to support the star and make it shine. It happens naturally once the core reaches the right conditions. During the sun's formation, gravity pulled material inward, and the centre became hotter and denser. At first, the forming sun glowed from the energy of contraction, but when the core became hot enough and dense enough, fusion began. From that point onward, the sun entered its long, stable life, supported by nuclear energy from within. It stopped being merely a collapsing ball of gas and became a main sequence star. There is a nice balance hidden in this. Fusion needs gravity to begin, because gravity compresses the core. But once fusion begins, it produces the pressure that resists gravity. Gravity is trying to pull everything inward. Fusion helps heat the core, and heat creates pressure that pushes outward. The sun exists because those tendencies balance each other. It is not an explosion, even though it releases immense energy, because gravity holds it together. It is not a collapse, even though gravity is always pulling inward, because fusion pushes back. The sun is like a long-held note, sustained between inward weight and outward pressure. Not a poetic note, perhaps, or of a very hot plasma note, but still beautifully steady. If fusion suddenly became much stronger, the sun would expand. As the core expanded, it would cool slightly, and the rate of fusion would ease. If fusion weakened, the core would contract under gravity, becoming hotter and denser, which would encourage fusion to increase again. This feedback keeps the sun stable. It is one of the reasons stars like the sun can shine so calmly for such long periods. The core is not balanced by luck, it is balanced by physical response. The sun adjusts through pressure and temperature, not quickly in a nervous way, but over timescales appropriate for a star, which is to say, not in a hurry and not especially concerned about your calendar. Fusion in the sun is also surprisingly gentle when measured per unit of material. This is a subtle but interesting point. The core as a whole produces an enormous amount of energy, but any small amount of the core produces energy rather slowly compared with, say, the power density of a human body or a compost pile. That sounds absurd at first. The sun seems powerful beyond comparison, but the sun is enormous. Its total output is vast because the core is vast, not because every bit of it is explosively intense. In that sense, the sun is not a bomb. It is a huge, steady, slow-burning nuclear system, though even the phrase slow burning is only a metaphor, because again, it is not burning, it is fusing. The difference matters. A bomb releases energy suddenly because conditions run away. The sun releases energy steadily, because gravity, pressure, and fusion hold one another in check. This is why the sun does not blow itself apart. A common question, once we learn that fusion releases so much energy, is why the sun is not simply exploding. The answer is that it is massive enough for gravity to confine the reaction, and the reaction proceeds at a controlled rate because the conditions regulate themselves. Fusion happens in the core, not everywhere at once throughout the sun. The energy moves outward slowly, and the star maintains a balance. There are eruptions on the surface and in the outer atmosphere, but those are magnetic events, not the core exploding. The deep fusion engine continues beneath them with extraordinary stability. The first successful steps of fusion in the core produce particles that quickly interact with the surrounding plasma. Energy is shared, scattered, absorbed, and re-emitted. The core is so dense that radiation cannot travel far before it meets matter again. This means the energy from fusion becomes part of the thermal life of the sun almost immediately. It heats the plasma, contributes to pressure, and begins the long outward journey that will eventually become sunlight. A single packet of energy does not leave the core with a clear label attached saying, "Made on Tuesday, please deliver to Earth." It becomes mixed into the vast interior activity of the star. By the time energy reaches the surface, it has been transformed so many times that its origin is not traceable in a simple way. Neutrinos are the exception. They are made in the fusion process and escape the sun with barely any interaction. Because they interact so weakly with matter, they do not get trapped in the core. They pass through the surrounding layers and fly into space almost at once. This makes them very useful to scientists. When we detect solar neutrinos on Earth, we are receiving direct evidence of fusion happening in the core right now, or at least as right now as anything can be when it has crossed the distance from the sun to Earth. They confirm that the sun's engine is operating as our models predict. For a long time, there was a puzzle because early experiments detected fewer solar neutrinos than expected. Eventually, scientists learned that neutrinos can change type as they travel, and the missing neutrinos were not missing after all. They had changed identity along the way, which is exactly the sort of behaviour one might expect from a particle that already passes through planets as if they are lace curtains. This story is a reminder that the sun has taught us not only about stars, but about particle physics as well. By trying to understand our nearest star, scientists discovered deeper truths about neutrinos themselves. The sun is both subject and instrument. It is a natural laboratory, producing particles and conditions that reveal how matter behaves at levels far removed from daily experience. When we look at sunlight, we see brightness. When scientists study the sun carefully, they see evidence about the deep rules of the universe. The fusion process also explains why hydrogen is so important cosmically. hydrogen was the most abundant element formed in the early universe, and it became the main fuel for the first long-lived stars. Stars are, in a sense, the universe's way of turning simple material into structure, light, and eventually heavier elements. The Sun is continuing that ancient work. It is taking hydrogen and building helium in its core. It is not massive enough to create the heaviest elements later in life, and it will not end as a spectacular supernova, but it is still part of the broader stellar story. Fusion is how stars shine, and how the universe gradually changes its chemical character. The Sun's quiet engine belongs to a cosmic tradition. The helium made in the Sun's core does not immediately float away or form balloons, although the thought of the Sun quietly filling party balloons at its centre is not the worst image for bedtime. The helium remains in the core, gradually building up over billions of years. Because helium nuclei are heavier than hydrogen nuclei, this changes the core's composition and behaviour over time. As the Sun ages, the core slowly becomes more helium-rich. This affects the balance of pressure, temperature, and fusion. The changes are subtle now, but they are part of the Sun's long evolution. Fusion is not only keeping the Sun alive in its present form, it is also slowly preparing the Sun for its future. The pace of that future is extremely slow by human standards. We do not need to worry that the Sun will stop fusing hydrogen next week, or next century, or even on any timescale relevant to civilization as we normally imagine it. The Sun has already been shining for billions of years, and has billions more years of stable hydrogen fusion ahead. Still, it is not eternal. Fusion consumes the hydrogen in the core gradually. The Sun is spending its fuel carefully, but it is spending it. This gives stars their life stories. A star begins, stabilizes, evolves, and eventually changes form because its nuclear fuel and internal structure change. The Sun's current calm is one phase, long and generous, but not endless. The energy released by fusion must go somewhere. Part of it helps maintain pressure in the core, supporting the Sun against gravity. Part of it begins moving outward through the radiative interior. But because the Sun is dense, this outward movement is slow. Photons are absorbed and re-emitted over and over, taking a path so indirect that calling it a path feels almost too organised. It is more like a wandering argument in a crowded room, with the point being passed around, misunderstood, restated, delayed, and eventually somehow arriving at the door. This long delay means that the Sun's surface glow is not a real-time broadcast from the core, in the way a lamp shines from a bulb. It is the surface release of energy that has spent a very long time inside. The quietness of fusion is also seen in how deeply hidden it is. We cannot look at the Sun and see fusion directly. The visible surface tells us about conditions where light escapes. The core remains concealed beneath opaque layers. Yet the whole star's existence points back to fusion. The balance of size, brightness, temperature, and lifetime all make sense only when nuclear fusion is included. Without it, the Sun would be a mystery. With it, the Sun becomes understandable, not simple, but coherent. The warmth you feel from sunlight is part of an enormous chain of cause and effect that begins with protons in the core overcoming repulsion through heat, pressure, and quantum probability. There is something almost humbling about how indirect it all is. The Sun's visible light is not born as visible light. The warmth on Earth is not produced for Earth. The fusion process does not happen with any purpose or drama. It simply follows the rules available to matter under extreme conditions. Yet from that purpose, free process, comes almost everything familiar on our world. Forests, plankton, weather, crop fields, ocean currents, vitamin production in skin, solar panels on roofs, and the comforting habit of turning one's face toward morning light all trace back to a nuclear process happening in darkness, buried inside plasma so dense that no human eye could ever see through it. Fusion in the Sun is sometimes described as hydrogen turning into helium, which is true, but the real process is not a single simple step. It involves intermediate particles and transformations. In the Sun's main pathway, protons combine through a sequence that includes the creation of a heavier form of hydrogen, the involvement of positrons, neutrinos, and eventually helium. The details matter to physicists, but the broad meaning is enough for our journey. The Sun takes simple nuclei under intense conditions and combines them into more stable nuclei, releasing energy in the process. It is nuclear alchemy, though not the old dream of turning lead into gold. It is the deeper and more natural transformation of matter into light. One reason this process is stable in the Sun is that the first step is rare. That rarity may sound like a weakness, but it is actually what allows the Sun to live long. If protons fuse too readily, the Sun would race through its fuel and shine far more intensely for a much shorter time. Life on Earth, if it appeared at all, would face a very different star. The slowness of the proton-proton chain is part of our good fortune. The Sun is bright enough to warm Earth, but not so furious that it exhausts itself quickly. Its quiet engine is quiet in exactly the way a habitable planet needs. Not motionless, not weak, but restrained. This restraint is built into the physical laws. The Sun does not choose moderation. It is moderated by the difficulty of fusion, the balance of pressure, and the structure of the star. Stars more massive than the Sun have hotter, denser cores, and can fuse their fuel much faster. They shine brighter and live shorter lives. Smaller stars fuse more slowly and can last far longer. The Sun sits between these extremes, bright and stable enough to support a living world over immense stretches of time. Its fusion rate is not just a technical detail, it is part of the reason Earth has had the time it needed. If we could somehow listen to the core, not with ears, but with instruments sensitive to its deep vibrations and particles, we would find no single moment of creation, no central spark that explains everything alone. Instead, we would find a continuous process spread through the inner region, a nuclear murmur beneath all sunlight. The core is alive with collisions, but the star as a whole appears steady because those events average together. This is one of nature's great smoothing acts. Individual particles behave probabilistically, but the enormous number of particles produces a reliable star. Randomness at tiny scales becomes stability at large scales. The Sun shines steadily because it contains enough microscopic uncertainty to make a macroscopic certainty. That idea is worth resting with for a moment. The light in your room depends on quantum events that cannot be predicted individually with certainty. Yet the overall sunlight is dependable enough to set clocks by, grow crops by, build calendars by, and complain about curtains by. Nature often works this way. The tiny world may be probabilistic, but large systems can become stable through sheer numbers. The Sun is an enormous example of this principle. It is not orderly because every particle follows a neat schedule. It is orderly because the crowd is vast and the average behavior is steady. As fusion continues, the Sun sends energy outward into the layers beyond the core. There, the story changes. The main question is no longer how energy is created, but how it travels. And this is not a simple journey. The Sun's interior is dense enough that radiation cannot stream freely. Photons are caught in a long wandering passage through the radiative region, repeatedly absorbed and re-released, shifted in energy, redirected in all directions, moving outward only by slow statistical progress. The energy born in the quiet engine does not immediately become the sunlight we see. It must first survive a journey through the star, a journey so slow and crowded that the final trip across space to Earth is almost nothing by comparison. The energy released in the Sun's core does not simply leap outward and become daylight. That would be far too straightforward for a star. It would be convenient, certainly. A little packet of light could be born in the core, point itself toward Earth, glide through the solar interior, pop out of the surface, and arrive at your window a few minutes later, perhaps with the quiet confidence of someone who found the fastest route on the first try. But inside the Sun, There is no clear road out. There is no open corridor, no empty tunnel, no polite sign saying this way to space. The core is crowded, dense and brilliant, and a photon born there begins its life in a place where light itself cannot travel very far without being interrupted. A photon is a tiny packet of light, or more broadly, a packet of electromagnetic energy. It has no little face, no tiny suitcase, and no opinion about where it is going, which is probably just as well, because its journey through the sun is not a journey that rewards planning. In the core, photons are produced with very high energy during nuclear fusion and related interactions. But almost as soon as they appear, they encounter charged particles in the surrounding plasma. The sun's interior is packed with free electrons and atomic nuclei, all moving, colliding, scattering and interacting. A photon does not get to sail through this environment like a beam through clear air. It is absorbed, scattered, redirected and transformed again and again. If sunlight had patience, it would need a great deal of it. This is one of the most important differences between the inside of the sun and the space outside it. Once a photon leaves the sun's visible surface, it can travel through space to Earth in just over 8 minutes, because space is mostly empty. That final part of the trip is direct and fast. But inside the sun, the photon's path is nothing like a straight line. It is more like a person trying to cross a busy room while being stopped every few centimeters by someone who wants to ask a question, hand them a teacup, turn them around, and send them in a different direction. After enough interruptions, the person may eventually reach the door, but it will not be because they walked neatly toward it. It will be because all the little steps, over a very long time, happen to add up to an outward drift. This kind of motion is often described as a random walk. The phrase is simple and it is useful. Imagine taking one step, then being spun around and taking another step in a random direction, then another, then another. Sometimes you move outward, sometimes you move sideways, sometimes you move inward again, which must be frustrating, though photons are spared the emotional burden. After many, many steps, there can be gradual progress away from the centre, but it is painfully slow compared with the speed of light in empty space. The photon itself always moves at light speed between interactions, but it is interrupted so often that its effective outward journey takes an enormous amount of time. This is why people sometimes say that the sunlight reaching Earth today began inside the sun thousands of years ago, or even much longer ago depending on how the journey is estimated. The exact time is not simple, because the energy changes identity many times. The original photon created in the core may not be the same photon that later escapes the surface. It may be absorbed by a particle, converted into thermal energy, then re-emitted as a new photon. That new photon may have a different energy, a different direction, and no memory of the old one. So when we talk about the journey of a photon, we are really talking about the journey of energy through the sun. The energy is passed along, scattered and reshaped, until at last some of it emerges as the visible sunlight that reaches us. This may sound like a technical detail, but it changes how we imagine sunlight. The light on your face is not a direct little message from the core. It is the final surface expression of energy that has been mixed, delayed, and transformed through the star. The sun is not like a lamp with a clear glass cover and a bulb inside. It is more like an enormous glowing crowd in which energy is passed from hand to hand, changed in the passing, and eventually released at the edge. By the time sunlight escapes, it has been softened from its original high-energy form into the broad mix of visible and invisible light that pours into space. The region just outside the core where much of this slow photon wandering takes place is called the radiative zone. It is not radiative because energy moves through it easily, but because radiation is the main way energy is transported there. The material is still extremely hot and dense, though less extreme than the core. Photons are repeatedly absorbed and re-emitted by particles in the plasma. The energy works outward, not through large rising currents, at least not mainly in this region, but through countless radiation interactions. It is a slow transfer. more like a rumour spreading through a packed hall than a messenger running across an empty field. In the radiative zone, the Sun's interior is stable enough that material does not overturn in huge boiling motions the way it does farther out. Temperature and pressure change with distance from the centre, and those conditions allow radiation to carry energy outward. But radiation transport in dense plasma is not graceful. It is efficient only in the patient way that a glacier is efficient. It gets there eventually. If you were expecting sunlight to be in a hurry, the radiative zone would gently disappoint you for a very long time. The photon's repeated interactions also change its energy. The energy produced in the core begins in very high energy forms, but as it is absorbed and re-emitted, it becomes part of the Sun's thermal environment. Energy is shared among particles, redistributed and gradually shifted toward lower energy light as it moves outward. This is why the light that finally leaves the Sun's surface is mostly the kind associated with the temperature of that surface, not the far more intense radiation born at the core. The Sun's interior acts as an enormous transformer, taking deep nuclear energy and turning it into the sunlight that can warm Earth without instantly sterilizing every picnic blanket. That last point is worth appreciating. The Sun's outer layers do not merely let energy out. They help determine the character of the energy that escapes. The visible surface has a temperature far lower than the core, though still fiercely hot by any earthly standard. The light emitted from that surface reflects those conditions. So the long journey outward is not just a delay, it is a conversion. The Sun turns nuclear energy into sunlight through layers of matter, pressure, radiation, and motion. What arrives at Earth is not raw core energy, it is star-processed light. The delay also helps make the Sun steady. Fusion in the core happens constantly, but any small fluctuations are smoothed out by the enormous amount of material the energy must pass through. Because energy takes so long to reach the surface, the Sun does not flicker wildly in response to every little change deep inside. Imagine a person whispering into one end of a vast crowded building, and by the time the message reaches the exit, it has been repeated so many times that tiny irregularities have blurred into a steady murmur. The Sun's surface shines with remarkable stability, in part because the interior is such a slow and complicated path. What might have been sharp changes become averaged into a calm glow. This is fortunate for Earth. Life depends not only on sunlight, but on sunlight that is reasonably steady. If the Sun's surface brightness changed dramatically from day to day because every core variation arrived immediately, Earth would be a much less comfortable place, and weather forecasts would be even more apologetic than they already are. Instead, the Sun's inner transport system spreads and smooths the energy over time. The star is powerful, but not erratic in its basic output. Its deep interior gives it a kind of thermal patience. There is another way to picture this. Suppose you drop a drop of ink into a thick sponge. It does not pass straight through and appear at the other side instantly. It spreads, twists through little passages, is held and released, slowed by the structure around it. Now replace the sponge with a sphere of hot plasma larger than anything in daily life. Replace the ink with energy, and make the whole thing shine by nuclear fusion. The comparison is imperfect, as all kitchen-friendly comparisons to stars must be, but it gives the feeling energy has to work its way through matter. The Sun is not empty inside, it is packed with resistance. As the energy moves outward, the conditions around it change. The plasma becomes less dense, the temperature drops, the pressure decreases, the particles are still energetic, but the environment is gradually less crowded than the core. Photons can travel a little farther between interactions, not freely yet, but with slightly longer pauses between interruptions. This does not suddenly make the journey easy, but it changes the character of transport. The deeper layers are dense and trapping. Farther out, the Sun begins to loosen its grip on radiation. The energy is still buried, but the door to space is no longer quite as unimaginably far away. Eventually, the radiative zone gives way to a region where radiation is no longer the best way to carry energy outward. The outer parts of the sun are cooler than the layers below, and the plasma becomes less transparent to certain forms of radiation. Energy begins to move more effectively through convection. That means hot material rises, carries energy upward, cools, and sinks again. But before we get into that great boiling motion, it is worth staying a little longer with the photon's radiative wandering, because it is one of the most counterintuitive parts of the sun's story. Light, the fastest thing there is, can be trapped by the very star that creates it. This trapping does not happen because the photon slows down in the usual sense. Between interactions, light still travels at light speed. The delay comes from the path, not from lazy light. A direct route outward from the core to the surface would take only a few seconds if the sun were transparent. But the sun is not transparent. Each interaction changes the direction. The path becomes tangled. The total distance travelled in all those random steps becomes vastly longer than the straight distance from core to surface. It is a little like trying to leave a large building but being required to bounce off every wall, chair and confused office plant before reaching the exit. This is why the final 8-minute trip to Earth is almost comically short compared with the internal journey. Once sunlight escapes the photosphere, space gives it room. It streams outward, spreading in every direction. A tiny fraction of it crosses Earth's path. Some reflects from clouds, some is absorbed by land and sea, some enters leaves, some warms your face, some slips through curtains and lands on a sleeping dog who accepts the energy without needing to understand radiative transfer. The same energy that took ages to work through the sun crosses the emptiness between sun and Earth in minutes. Inside the star, light is trapped by matter. Outside the star, light is free. The photon's journey also tells us why the surface of the sun is the surface we see. The photosphere is the layer where the sun becomes transparent enough for light to escape. Below it, photons are still likely to be absorbed or scattered before travelling far. Above it, the gas is thin enough that many photons can stream away into space. This does not mean the sun has a hard edge. It means there is a transition from opaque plasma to transparent space. The visible surface is where the long random walk ends and the direct journey begins. It is the release point, not the birthplace. This is important because when we look at the sun, we see only the light that last interacted with matter near the photosphere. We do not see the core directly. We do not see the radiative zone directly. We infer them from models, vibrations, neutrinos, and the physics of matter under pressure. The sun's bright face hides its interior as effectively as a fogged window hides a room. The light we receive has escaped from the outer visible layers, but it carries the consequences of deep processes. It is both revealing and concealing. It tells us the sun is hot and luminous, but it does not show the full path it took to become so. The fact that energy changes form along the way also means that asking where a particular sunlight photon was born can be slippery. The photon entering your eye may have been emitted from the photosphere, but the energy behind it came from fusion in the core. That energy may have passed through many photons and particles before becoming the one that finally escaped. It is like asking where a story began when it has been retold for generations. The sentence you hear now may be new, but the meaning has an ancestry. Sunlight has ancestry. Its immediate source is the surface, but its deep source is the core. There is a calmness in this layered picture. The sun is not a simple line from fusion to light. It is a system. The core makes energy. The radiative zone slows and redistributes it. The outer layers carry it through motion. The photosphere releases it. Space delivers it. Earth receives it. Each stage matters. Remove any part of the chain, and the sun as we know it would not exist. Even the delay is part of the story. The sun shines steadily because energy must pass through the star's deep interior before it can leave. Scientists understand the photon journey through a combination of physics, observation, and modelling. They study how radiation interacts with plasma, how temperature and density change inside the sun, and how the sun vibrates. Those vibrations, tiny motions on the surface caused by waves travelling through the interior, allow scientists to infer what the inside is like. This field is similar in spirit to studying earthquakes to learn about Earth's interior, though in the sun the waves travel through plasma rather than rock. By listening to how the sun rings, scientists can test their understanding of the hidden layers. The photon may take a long time to escape, but the sun's vibrations provide another way to probe what lies beneath. There is also the matter of trust. We cannot scoop out a sample of the radiative zone and place it politely on a laboratory table. We cannot lower a thermometer into the core. Our understanding comes from the way many pieces of evidence fit together. The sun's mass, brightness, surface composition, neutrinos, vibrations, and the known laws of physics all point to a consistent interior structure. This is one of the quiet strengths of science. It often understands hidden things by their effects. We do not need to see the core directly to know it is there. We know it because the sun shines, because neutrinos arrive, because the surface vibrates in specific ways, and because models that include fusion and radiation transport match what we observe. The journey of solar energy outward is also connected to the colour and warmth of sunlight. By the time energy reaches the photosphere, it emerges in a range that includes visible light, infrared light, and ultraviolet light. Visible light is what our eyes detect. Infrared is felt as heat. Ultraviolet has enough energy to affect molecules in skin and atmosphere. Earth's atmosphere filters much of the more harmful ultraviolet, though not all of it, which is why sunscreen has its place in the story of stellar physics. It may not sound grand to say that a bottle of sunscreen is related to the photon journey through the sun, but it is. Everyday life is full of small negotiations with starlight. Plants make one of the most important negotiations. They use visible sunlight for photosynthesis, turning carbon dioxide and water into sugars and releasing oxygen. The photon that reaches a leaf is part of an ancient chain from core fusion to radiative wandering, to surface escape to space travel to biological chemistry. It is hard to think of a more remarkable commute. A photon leaves the sun, crosses space, strikes a molecule in a leaf, and helps move energy into the living world. Later, that energy may become food, movement, thought, or warmth. Sunlight does not just illuminate Earth, it enters Earth's systems. And yet most photons leaving the sun never meet Earth at all. They stream into space in every direction. Earth is a tiny target. The portion we receive is incredibly small compared with the sun's total output. But that small portion is enough. Enough to run the weather, feed ecosystems, drive the water cycle, and remind people on bright mornings that dust is far more visible than expected. The sun is generous in the sense that it sends light everywhere, not in the sense that it knows we are here. We live in the path of a tiny spill of stellar energy, and that spill has shaped nearly everything familiar. The photon's long interior journey also gives sunlight a kind of hidden age. The light may have left the surface minutes ago, but the energy behind it may have been buried in the sun since long before human memory. This means daylight is both fresh and old. Fresh because the photons reaching you have just crossed space from the photosphere. Old because the energy they carry has slowly migrated from the core over immense spans of time. Morning sunlight can feel immediate, and it is, but it also carries the history of a long escape from the centre of a star. That is not mystical. It is just the consequence of dense plasma and radiation transport, which is somehow more satisfying. As energy nears the outer regions of the sun, the rules begin to shift. Radiation has done much of the work through the deep interior, but farther out the plasma becomes arranged in a way that favours bulk motion. Hot material can rise, cooler material can sink. Energy that once moved by being passed through photons begins to travel by being carried in moving plasma. This transition brings the sun closer to something that feels familiar, because convection also happens in boiling water, in warm air rising from a heater, and in soup if you watch it instead of stirring. Of course, in the sun, the soup is electrically charged plasma, the pot is gravity, and the stove is a nuclear core, so the comparison should not be pushed too far while making dinner. Still, it is the next necessary step. The energy born in fusion and delayed by radiative wandering eventually reaches layers where the sun begins to churn. There, the outward flow becomes visible in a new way. The surface patterns we can observe, the grainy texture of the photosphere, the rising and falling cells of hot plasma, all connect to convection beneath. The photon's long hidden journey is nearly over, but before light finally escapes into space, the sun's outer interior carries energy upward through vast boiling motions, turning the steady output of the core into the restless textured face of a living star. By the time the sun's energy has wandered outward through the dense inner regions, it reaches a place where the old method of travel becomes less useful. Deep inside, radiation has carried energy from particle to particle, with photons absorbed, scattered, and recreated over and over again. But farther from the center, the sun's material changes. It becomes cooler compared with the interior, though still unimaginably hot by anything we would call normal. It becomes less dense, more able to move in great rising and sinking currents. And here, beneath the visible face of the sun, the star begins to behave in a way that feels almost familiar. It starts to boil. Not boiling in the ordinary kitchen sense, of course. There is no water, no bubbles of steam, no saucepan rattling gently on the hob, while someone wonders whether pasta counts as dinner again. The sun's outer interior is made of plasma, a hot electrically charged gas of free electrons and atomic nuclei. But the basic idea of convection is familiar. Hot material rises, cooler material sinks. Energy is carried upward by motion. You can see a mild version of it in a pot of soup warming on a stove, where warmer liquid from below rises toward the surface, spreads out, cools and sinks back down. You can feel it in a room heated by a radiator, where warm air climbs and cooler air settles lower. Inside the sun, the same principle is happening on a scale so large that the comparison becomes both useful and slightly ridiculous. Imagine a pot of soup wider than worlds, made of glowing plasma stirred by gravity, heated from below by a nuclear core, and threaded by magnetic fields that behave like invisible ropes. That is closer to the sun's convective region, though still much too tidy. This outer layer is called the convection zone. It lies below the sun's visible surface and above the deeper radiative zone. In this region, energy is transported mainly by the movement of hot plasma. The plasma near the bottom of the convection zone absorbs energy from below and becomes buoyant. Because it is hotter, it expands slightly and becomes less dense than the material above it, so it rises. As it rises, it carries energy upward. Nearer the surface, it cools by releasing energy, becomes denser, and begins to sink again. This cycle repeats continuously, creating vast currents that churn beneath the surface. The sun's outer layers are not sitting still like a glowing shell. They are moving, overturning, rising, falling, and folding energy through themselves in a restless pattern. The reason convection takes over has to do with how matter interacts with radiation at these temperatures and densities. In the deeper radiative region, photons can carry energy outward through repeated interactions. It is slow, but it works. Farther out, the plasma becomes less able to let radiation carry energy efficiently by itself. Certain atoms and ions can absorb light more strongly under these conditions, which makes radiation transport less effective. When energy cannot escape easily by photons alone, the material itself starts to move. It is as if the sun says, in its wordless physical way, if the light cannot get out quickly enough, the plasma will carry the heat upward instead. Not a decision, of course. Stars are not known for their committee meetings. It is simply the natural response of hot fluid under gravity. The convection zone is enormous by human standards. Its depth extends through a significant portion of the sun's outer radius, yet compared with the whole sun, it is still only one region in a layered structure. It is not where nuclear fusion happens. It is not the birthplace of energy. Its job is transport. The core makes the energy, the radiative zone passes it outward slowly, and the convection zone takes over near the outer part of the Sun, carrying energy by motion until it reaches the visible surface. This is one of the great themes of the Sun. Different regions have different roles. The star is not the same all the way through. It is organised by pressure, temperature, density, and how energy can move. The rising and sinking motions in the convection zone produce patterns that can actually be seen on the Sun's surface. Through telescopes designed to observe the Sun safely, the photosphere often appears grainy, covered in small bright cells with darker edges. These are called granules. Each bright granule is the top of a rising column of hot plasma. The darker edges are where cooler plasma sinks back down. To us, seen from millions of kilometers away, these granules look delicate and fine, like the texture of orange peel or the surface of porridge just before one worries it may be too hot. But each granule is enormous, often comparable in size to a country. The Sun has a way of making huge things look small, mostly by being inconsiderately large. Granulation is one of the visible signs that the Sun is alive with motion. The surface is not smooth, it is not still. It is a constantly changing pattern of convection cells, appearing, shifting, and fading over minutes. Hot plasma rises, spreads, cools, and sinks. Another cell takes its place. This activity gives the visible Sun a textured look, though we should never look directly at it without proper solar filters. The Sun is generous with light, but it is not gentle with unprotected eyes. With the right instruments, however, we can watch the outer layers churn in real time. We can see that the Sun's apparent calm is a trick of distance. Below the small granules are larger patterns as well. The convection zone includes motions across many scales. Some flows are relatively small and short-lived. Others are broader and more persistent. The Sun contains giant circulation patterns that move plasma across latitudes and depths. These flows are tied to the Sun's rotation and magnetic behaviour. The convection zone is not just boiling upward and downward, it is also shearing, twisting, and circulating. The Sun rotates, but not like a solid ball. The equator rotates faster than the regions nearer the poles. This uneven rotation stretches and winds magnetic fields, helping create the complex solar magnetic cycle. So the boiling layers beneath the surface are not merely carrying heat, they are helping shape the Sun's magnetic personality. This is where the Sun becomes especially unlike a simple glowing sphere. Because the material is plasma, its motion affects magnetic fields, and magnetic fields affect its motion. In a normal pot of soup, the soup does not drag magnetic fields around in any important way, unless your cooking has taken a deeply unusual turn. In the Sun, charged particles moving together create electric currents, and electric currents are linked with magnetism. The plasma and magnetic field are coupled. As the plasma rises, sinks, rotates, and circulates, it pulls and stretches magnetic field lines with it. Over time, those fields can become twisted and concentrated. They can emerge through the surface as sunspots. They can store energy and release it suddenly as flares. They can launch great clouds of plasma into space. Much of the Sun's visible drama begins with the hidden motion below. The convection zone is therefore not just a transport layer, it is also a magnetic workshop. The Sun's magnetic field is generated and maintained by motion inside the star, especially by the interaction of convection and rotation. This process is often called a dynamo, because moving charged plasma can sustain magnetic fields. The exact details are complex and still studied actively, but the broad idea is clear. A rotating, convecting plasma body can build magnetic structure. The Sun's 11-year activity cycle, with sunspots increasing and decreasing, is tied to this internal magnetic behaviour. Beneath the visible surface, the Sun is winding up its own magnetic fields like a ball of invisible thread. though the thread sometimes snaps back in spectacular ways. It is worth taking a moment to picture the physical experience of the convection zone, even though no one could experience it directly. The plasma is hot enough to glow. It is dense compared with Earth's atmosphere, though far less dense than the deeper interior. It moves in great currents, rising and falling under gravity. The pressure is immense, though lower than deeper layers. The environment is turbulent, meaning motion is irregular and chaotic across many scales. Turbulence is familiar in rushing water, storm clouds, smoke, and air behind a moving vehicle. In the Sun, turbulence is made of plasma and heat. It mixes energy, twists magnetic fields, and creates patterns that are never exactly repeated. Turbulence can sound messy, and it is, but it is not meaningless. It has structure. Large flows break into smaller flows. Small motions combine with larger circulation. Patterns form and vanish. Energy cascades through scales. The Sun's outer interior is not chaotic in the sense of random nonsense. It is chaotic in the sense of deeply complicated motion governed by physical laws. The result is a surface that flickers with granules, magnetic regions, and waves. If we could speed up the Sun's surface in a safe and sensible recording, it would look like a living texture, a bright cellular ocean in constant motion. The word ocean is useful, though again not literal. The Sun's convection zone behaves a little like a vast ocean of plasma, with currents, waves, and storms. But unlike Earth's oceans, it has no solid bottom in the ordinary sense, and no air above it in the ordinary sense. It grades into other solar layers. Its motion is driven by heat from below and cooling near the surface. The top of the convection zone is where energy can finally escape efficiently as radiation. The plasma rises, releases heat near the photosphere, then sinks. This overturning motion is the Sun's way of moving energy through the final interior stretch before light is released into space. This process also produces sound waves inside the Sun. The churning plasma excites waves that travel through the solar interior, making the Sun ring. These waves cause tiny motions at the surface that can be measured. Scientists use them to study the interior in a field called helioseismology. It is similar in spirit to how geologists use earthquake waves to understand Earth's interior, except the Sun is not a rocky planet but a glowing plasma sphere, and the waves are generated by continuous convection rather than occasional cracking crust. By studying how the Sun vibrates, scientists can infer the speed of sound inside it, the depth of the convection zone, the rotation of internal layers and other hidden properties. So the boiling motions beneath the surface do more than carry heat. They make the Sun hum with information. There is something pleasing about the idea that the Sun can be listened to, not with ordinary ears because sound cannot cross the vacuum of space, but through measurements of its surface motions. The Sun rings like a bell, though a very large bell that no one should attempt to polish. Its vibrations reveal its hidden layers. Those vibrations are shaped in part by convection, by the constant motion of hot plasma. In a way, the boiling outer layers are both engine room and orchestra section, stirring the star and sending waves through it. The surface trembles with clues. The convection zone also explains why the Sun's surface has a limited and changing texture, rather than a perfectly even glow. If energy emerged smoothly everywhere at once, the photosphere might appear uniform. Instead, the surface is broken into bright and dark patterns, because energy is carried upward in cells. Bright areas mark hotter rising material, darker lanes mark cooler sinking material. The difference in brightness is not like black and white. The darker areas are still extremely bright and hot. They only look dark compared with the hotter regions around them. This is a common theme in solar observation. What looks dark on the Sun is often still dazzling by earthly standards. A sunspot, for example, looks dark because it is cooler than its surroundings, but if you could place it alone in the night sky, it would still shine brilliantly. The Sun makes even its shadows bright. As plasma rises toward the surface, it expands because pressure is lower higher up. Expansion cools it. This cooling helps it become denser and sink again. This cycle is continuous. Hot upflows bring energy toward the surface. Cooler downflows return material deeper into the convection zone. The plasma does not travel in neat little loops like diagrams in textbooks, though diagrams are helpful. Real convection is messy. Flows split, merge, twist, and shear. But the overall pattern persists because the physics behind it persists. Heat below, cooling above, gravity throughout. That combination produces overturning motion. Rotation complicates the motion further. The sun's differential rotation means different latitudes spin at different rates. The equator takes less time to rotate than the poles. Because the sun is plasma rather than solid rock, it can rotate this way. The convection zone participates in this uneven rotation, and the shear between different regions helps stretch magnetic fields. There is also a transition region near the base of the convection zone where rotation changes in an important way. Scientists believe this region plays a significant role in the solar dynamo. It is one of the hidden places where the sun's large-scale magnetic field may be organized and strengthened. We cannot see it directly, but we can study its effects. This hidden magnetic generation is important because the sun's surface behavior affects Earth. Sunspots, flares, and solar storms are all tied to magnetic activity. The charged particles and radiation from strong solar events can influence satellites, radio communication, power grids, and astronauts beyond Earth's protective atmosphere. So the boiling layers beneath the sun's surface are not remote curiosities. Their motion helps set the rhythm of space weather. A twist in plasma far beneath the visible surface can eventually contribute to an eruption that reaches across the solar system. The sun's outer interior is connected to the technological world in which we live, even if most of us do not think about solar magnetism while checking a weather app. The convection zone also affects the transport of material. The sun is mostly hydrogen and helium, but heavier elements are mixed through parts of its outer layers by convective motion. In stars, convection can stir material, bringing some elements upward and carrying others downward depending on conditions. In the sun, the outer convective envelope is one reason the photosphere gives us useful information about the sun's composition. The light from the surface carries signatures of elements present there. By studying the spectrum of sunlight, scientists can identify what the sun is made of. The churning outer layers help make that surface composition representative of a larger mixed region, though not necessarily of the entire deep interior where fusion has altered the core. Spectroscopy is one of the great tools of astronomy. When sunlight is split into its colours, it contains dark lines where specific wavelengths have been absorbed by atoms and ions in the sun's atmosphere. Those lines reveal chemical composition, temperature, motion, and magnetic fields. It is astonishing that light, after its long journey from the sun, can still carry so much information. A beam of sunlight is not just illumination. It is a record if you know how to read it. The convection zone helps shape the conditions from which that record emerges. Near the surface, convection becomes more visible and more efficient at releasing heat. The rising plasma reaches the photosphere, radiates energy into space, cools, and descends. This creates the granulation pattern mentioned earlier, but the pattern is not frozen. Individual granules live for only a short time. They appear, broaden, fade, and are replaced. The surface of the sun is being renewed constantly by material from below. When you look at the sun through safe instruments, you're not looking at a permanent face. You're looking at a moving skin of light, refreshed by the boiling layers beneath it. This idea is lovely in a practical way. The sun's visible face is not a painted surface. It is the top of a convective process. The light we see comes from material that has recently carried energy upward, released it, and begun to sink or spread. The photosphere is where the long internal journey of energy turns into outward radiation. Beneath it, convection delivers energy to the edge. Above it, photons escape into space. The surface is a boundary between trapped energy and free light. There is a kind of quiet violence in this region, though the phrase must be used carefully. The motions are powerful, the temperatures extreme, the magnetic fields intense, but the overall result from Earth is a steady disk of sunlight. This is another example of distance smoothing reality. From here, the sun seems calm enough to be represented by a small icon on a forecast screen. Up close, its surface is a restless sea of plasma cells, magnetic loops, bright patches, dark spots, and sudden eruptions. The difference between those two views is not contradiction. It is perspective. A storm cloud from far away may look like a soft grey smudge. Inside it, air is rising, water is condensing, ice is forming, charges are separating, and lightning may be preparing itself with poor manners. The sun is similar, but on a scale that makes storm clouds seem like shy little handkerchiefs. The convective motions beneath the surface also contribute to the sun's mottled brightness. In some regions, magnetic fields suppress convection. Where strong magnetic fields emerge through the photosphere, they can prevent hot plasma from rising as effectively. Those regions become cooler than their surroundings and appear as sunspots. This is one way the hidden motion below connects directly to visible features above. A sunspot is not a hole, and it is not a stain on the sun. It is a magnetic region where convection is inhibited, creating a cooler patch against the brighter surface. Even there, the temperatures are still enormous. The darkness is relative, like a slightly dimmer bulb held next to a floodlight. The sun's magnetism can also create bright regions, loops, and active areas. Plasma follows magnetic field lines, forming arches that rise above the surface. The convection zone helps twist and stress these fields from below. When magnetic energy is suddenly released, flares can occur. The sun's outer atmosphere can be disturbed dramatically, and charged particles can be accelerated into space. All of this begins, in part, with the convective and rotational motions beneath the surface. The boiling layers are not just hidden plumbing, they are active participants in the sun's changing behaviour. If the sun did not have a convection zone like this, it would look and behave differently. Energy would still need to move outward somehow, but the surface texture, magnetic generation, and activity cycles would not be the same. Stars of different masses have different internal structures. Some are convective in their outer layers like the sun. Some are convective in their cores. Some are convective throughout. The way a star transports energy shapes its life and appearance. Our sun's convection zone is one part of why it has the kind of magnetic cycle and surface behaviour we observe. It is easy to forget that all of this is happening constantly. While you sleep, the sun's convection zone churns. While clouds cover the sky, hot plasma rises and cool plasma sinks. While the night side of Earth turns away from the sun, the star keeps boiling beneath its visible face. Its motion does not pause when we cannot see it. The surface facing us changes as the sun rotates, bringing different features into view, but the interior activity is continuous. The sun is not a daytime object. It is always there, always working, always stirring itself beneath the light. The boiling layers beneath the surface are where the sun begins to look more like a living system, though it is not alive. It has circulation, rhythm, cycles, and storms. It has hidden currents that shape visible behaviour. It has a surface renewed from below. These qualities make it tempting to use biological language, and while we should be careful not to imagine intention, the analogy helps us feel the complexity. The sun has a kind of physical metabolism. Fusion produces energy, layers transport it, convection circulates it, the surface releases it, magnetic fields store and discharge it. Everything is connected. As the energy reaches the top of the convection zone, it arrives at the region we actually see. The visible face of the sun, the photosphere, is not a solid surface but a glowing layer where photons can finally escape after their long internal struggle. It is patterned by the convection beneath it, brightened by rising plasma, darkened in places by sinking lanes and magnetic fields, and constantly refreshed by motion. This is the layer that sends sunlight across space. It is the face the sun shows us, calm from afar and restless up close, and it is where the journey from hidden nuclear energy becomes the light that fills our sky. After the long climb through the sun's interior, after the energy has been born in the core, delayed through the radiative depths, and carried upward by the rolling motions of convection, it finally reaches the layer we can actually see. This is the photosphere, the visible face of the sun. It is the part that gives the sun its familiar round outline in the sky, the part that seems to shine as a smooth, bright disk, the part that makes shadows, warms stones, glitters on water, and sneaks through curtains just early enough to remind you that sleep and daylight are not always on speaking terms. When we look at the sun, safely and with proper instruments, we are mostly looking at the photosphere, not the core, not the deep interior, not the whole star at once, just the thin outer layer from which light finally escapes into space. Calling it a face is useful, but it can also be misleading. The photosphere is not a solid surface. You could not land on it. You could not walk across it with a flag and a very optimistic pair of boots. It is a layer of hot plasma, a region where the sun changes from being mostly opaque to being transparent enough for light to leave. Below the photosphere, photons are still likely to be absorbed or scattered before they get very far. Above it, many photons can travel freely outward. This is why it appears to us like a surface. It is the last place where much of the light has interacted with solar material before beginning its journey through space. It is less like the ground beneath your feet and more like the glowing surface of a fog bank, the place where the fog finally thins enough for light to come through. The photosphere is thin compared with the full size of the sun, but thin is a relative word when the object under discussion is a star. Even so, it is only a very shallow layer in solar terms. Most of the sun lies beneath it, hidden from ordinary sight. This is a little like looking at the surface of the ocean and trying to understand the whole sea from the glittering top layer. The surface tells you a great deal, but it is not the entire story. It shows motion, brightness, temperature, and sometimes disturbances rising from below. But the deep structure remains concealed. The photosphere is the sun's visible skin, and like skin, it reveals clues about what is happening underneath without showing everything directly. Its temperature is far cooler than the core, though still fiercely hot by any earthly standard. The visible surface is hot enough to glow white, sending out light across the visible spectrum along with infrared and ultraviolet radiation. From the ground, our atmosphere often makes the sun appear yellow, orange, or red, especially when it is low near the horizon. But the light from the photosphere itself is closer to white, a mix of many colours blended together. Our eyes and our atmosphere turn it into the familiar warm disk of daylight. The difference is a reminder that we never see the sun from nowhere. We see it through air, through scattering, through the limits of our eyes, and very often through the emotional state of whether we have had enough breakfast. The brightness of the photosphere is so intense that direct viewing is dangerous. This is not a small caution tucked politely at the edge of the subject. It matters. The sun can damage eyesight very quickly, even when it does not feel painful at first. Safe solar observation requires proper filters designed for the task. Ordinary sunglasses are not enough. Looking through a telescope or binoculars without the correct solar filter is especially dangerous because lenses gather and focus the light. The sun is beautiful, but it is not casual. It asks, in its silent, stellar way, to be respected. With the right instruments, however, the photosphere becomes a rich and detailed place. Instead of a perfectly smooth disk, it appears textured. The surface is covered with granules, small bright cells surrounded by darker lanes. These granules are the visible tops of convection currents. Hot plasma rises from below, reaches the surface, releases energy as light, spreads outward, cools, and then sinks along the darker edges. To human eyes at a safe distance, the pattern can look delicate, almost fine-grained. But each granule is enormous, large enough that if placed on Earth it could cover a large region. The Sun makes vast structures look small because the whole star is so much larger still. It is rather like looking at the texture of a loaf of bread from across a field if the loaf were a star and the crumbs were wider than cities. Granulation is one of the clearest signs that the photosphere is not still. It is constantly renewed from below. Individual granules appear and fade over short times, replaced by new rising cells. The visible surface is a moving pattern, a bright, restless layer shaped by energy coming up from the convection zone. Although the Sun may seem steady from Earth, the photosphere is changing every moment. Its calm appearance is a gift of distance. Up close, it is an ocean of glowing plasma, rising and sinking, flashing and dimming, organised by heat and gravity into a living texture without life. The darker lanes between granules are not truly dark. They're only darker by comparison. They still shine with tremendous brightness. This is a useful thing to remember about solar features in general. On the Sun, dark often means slightly cooler, not cold, not dim in an ordinary sense, and certainly not safe. A dark patch on the photosphere can still be brighter than almost anything we normally experience. Our eyes and instruments compare one part of the Sun to another, and because the surrounding surface is so bright, cooler regions can look black or grey. The Sun's shadows are still made of light. The photosphere also shows a gentle darkening near the edge of the solar disk, an effect called limb darkening. When we look at the centre of the Sun's disk, we are seeing somewhat deeper into the photosphere, where the gas is hotter and brighter. Near the edge, our line of sight passes through the upper cooler parts of the photosphere, so it appears slightly dimmer. This is not because the edge of the Sun is actually fading away like an old lamp. It is because we are viewing the glowing layer from a different angle. The Sun is a sphere, and the photosphere has depth. The change in brightness across the disk tells scientists about temperature and structure in that visible layer. Even the way the Sun darkens toward its rim is a clue. The photosphere is also where sunlight gains the fingerprints that reveal the Sun's composition. When sunlight is spread into a spectrum, it does not form a perfectly smooth rainbow. It contains many dark lines, places where specific colours are slightly missing, because atoms and ions in the solar atmosphere absorb light at particular wavelengths. These lines are like signatures from different elements: hydrogen, helium, iron, calcium, sodium, and many others leave recognisable patterns. By reading these lines, scientists can tell what elements are present in the photosphere. This is one of astronomy's greatest achievements. We cannot touch the Sun, bottle it, or bring home a polite sample in a jar, but we can read its light and learn what it is made of. This technique, spectroscopy, turned sunlight into a message. It showed that stars are not unknowable points of brightness. Their light carries information about temperature, motion, pressure, magnetic fields, and chemistry. The photosphere is the main source of the visible sunlight we analyse, so it acts like the Sun's speaking surface. The Sun does not speak in words, which is probably for the best because a star that large might have a rather overpowering indoor voice. It speaks in spectra, in lines and shifts and brightness patterns. Scientists learn to read those patterns and reconstruct the physical conditions that produce them. One of the most famous elements connected to the Sun is helium. Helium was first detected in the Sun's spectrum before it was found on Earth. Its name even comes from the Sun. That is a wonderful detail, because it shows how studying the photosphere and its light can reveal things not yet known in laboratories on our own planet. The Sun was not merely confirming what people already knew, it was teaching. A distant glowing surface, observed carefully, revealed an element hidden in plain sight above us. Later helium was discovered on Earth as well, but the Sun had already introduced it. The photosphere is not only bright and textured, it is also in motion in many ways at once. There are upward and downward flows from granulation. There are larger scale flows across the surface. There is rotation, with the equator turning faster than the higher latitudes. There are oscillations, waves that make the surface rise and fall slightly. These motions can be measured by observing tiny shifts in the light. If part of the solar surface moves toward us, its light is shifted slightly one way. If it moves away, it is shifted another way. These changes are very small, but with precise instruments they reveal the motion of solar material. The photosphere is not a painted disk, it is a moving, vibrating plasma layer. The sun's vibrations are especially important because they let scientists study the hidden interior. The photosphere rises and falls with waves travelling through the sun. These waves are shaped by the conditions inside, so measuring them allows scientists to infer the structure and motion of deeper layers. It's a bit like listening to a musical instrument and learning about its shape from the sound it makes. The sun rings continuously, and the photosphere is where that ringing can be observed. Every small ripple at the surface is part of a deeper conversation inside the star. The photosphere is also the stage on which sunspots appear. Sunspots are darker regions caused by strong magnetic fields that interfere with convection. Because hot plasma cannot rise as freely in those areas, the surface there becomes cooler than the surrounding photosphere. Cooler means darker by comparison, though still intensely bright in ordinary terms. Sunspots often appear in pairs or groups, reflecting the structure of magnetic fields emerging through the surface. They can last for days, weeks, or sometimes longer. Their number rises and falls in a cycle tied to the sun's magnetic activity. So when we observe sunspots on the photosphere, we are seeing magnetic fields from below breaking through into visibility. Sunspots were among the first clues that the sun was not perfect and unchanging. Early telescopic observers saw dark marks moving across the solar disk as the sun rotated. This challenged older ideas of the heavens as flawless and fixed. The sun had blemishes. It changed. It rotated. Its surface was active. That realization was not just an astronomical detail. It was part of a broader shift in how people understood the sky. The sun was no longer a perfect golden emblem. It was a physical object with motion, structure, and weather of its own. The photosphere made the sun real in a new way. Of course, sunspots are not flaws in any moral or aesthetic sense. They are magnetic regions, natural and informative. They tell us where magnetic fields are strong. They often mark active regions where flares and eruptions may occur. Around sunspots, the photosphere can become more complex with bright patches and twisted structures. These active regions connect the visible surface to the atmosphere above and the convection zone below. The photosphere is not isolated. It is the boundary where interior dynamics and outer solar activity meet. The magnetic fields that shape sunspots are invisible directly, but their effects are visible. They cool regions by suppressing convection. They alter spectral lines in ways that reveal field strength and direction. They guide plasma into loops that rise above the surface. They store energy that can later be released explosively. In this sense, the photosphere is like a screen on which hidden magnetic processes cast their shadows and highlights. By watching it carefully, scientists can anticipate some forms of solar activity, though the sun remains complicated enough to resist perfect prediction, as if it has taken a personal interest in keeping space weather forecasters humble. The photosphere also produces small, bright magnetic features called faculae. These are brighter regions often seen near sunspots or toward the edge of the solar disk. They are associated with concentrated magnetic fields and can increase the overall brightness of active regions. Sunspots darken parts of the surface, while faculae brighten others. Over the solar cycle, the balance between these features slightly changes the sun's total energy output. The effect is small but measurable. The sun is steady but not perfectly constant. Its visible face subtly changes as magnetic activity rises and falls. This slight variability matters because the sun is the main energy source for Earth's climate system. The changes in total solar brightness over the activity cycle are modest. far too small to explain modern rapid warming, but they are part of the natural background of solar influence. Understanding the photosphere helps scientists separate solar changes from other causes of climate change. The sun is not just a symbol in the sky, it is a measured physical input to Earth's environment, and the photosphere is where that input becomes visible light. The photosphere also defines the apparent size of the sun in our sky. The sharp edge we see is not a solid boundary, but the point where light can escape from a relatively narrow layer. The sun's atmosphere extends above it, becoming the chromosphere and then the corona, but those layers are much thinner and fainter in visible light under ordinary conditions. During a total solar eclipse, when the moon blocks the bright photosphere, the outer atmosphere becomes visible. This is one reason eclipses are so scientifically valuable and so emotionally striking. The photosphere is so bright that it normally hides the delicate structures above it. Cover the visible face, and suddenly the sun's outer atmosphere appears, like a secret revealed only when the main spotlight is dimmed. The photosphere's brightness also explains why the sky is blue during the day. Sunlight from the photosphere enters Earth's atmosphere, where shorter wavelengths are scattered in all directions by air molecules. This scattered light fills the sky, making daytime blue. At sunrise and sunset, sunlight passes through more atmosphere, and more of the shorter wavelengths are scattered away from the direct beam, leaving warmer reds and oranges. So even the colour of the sky is connected to the photosphere, filtered through Earth's air. The sun's visible face and our planet's atmosphere collaborate to make the daily theatre of morning and evening. Neither is trying to be artistic, but the result is hard to complain about. The photosphere is also where the sun's energy finally becomes practical for us. Solar panels absorb photons that last emerge from this layer. Plants use light from this layer. Our eyes evolved under light from this layer. The rhythms of day and night depend on Earth rotating beneath light from this layer. Even fossil fuels formed from ancient organisms that captured sunlight long ago are connected to the photosphere. It is the release surface for the energy economy of Earth. Every beam that powers life and weather has passed through this visible face. Yet the photosphere itself is only the start of sunlight's final journey. Once photons escape, they travel outward in straight lines unless something intercepts or redirects them. Most leave the solar system entirely. A tiny fraction reaches Earth. Some bounce off clouds and snow, some plunge into oceans, some warm soil. Some enter human eyes and become the perception of daylight. The photosphere produces light in all directions with no preference for Earth, and Earth receives just enough to make its surface alive and changeable. This is one of the strange comforts of astronomy. Our world depends on a small fraction of a star's ordinary output. The visible face of the sun also changes with time. Over minutes, granules shift. Over days, rotation carries features across the disk. Over weeks and months, active regions grow and decay. Over years, the number of sunspots rises and falls. Over billions of years, the sun's overall brightness slowly increases as its core evolves. The photosphere reflects some of these changes, especially the shorter-term surface and magnetic ones. It is not a static mask. It is a moving record of the sun's current state. When we describe the photosphere as the visible surface, we're using the language of appearance. Physically, it is a layer where opacity drops enough for light to escape. The idea of opacity is simply how difficult it is for light to pass through material. In the deeper sun, opacity is high. Light is trapped. In and above the photosphere, opacity becomes low enough that light can stream away. This transition gives the sun its apparent edge. It also means that the sunlight we see comes from slightly different depths depending on colour and viewing angle. The photosphere is not a single razor-thin line. It has thickness and structure. Like many natural boundaries, it is more of a gradual change than a strict border. This helps explain why the photosphere can be studied in layers. Different wavelengths of light can reveal different heights and conditions. Some spectral lines form higher in the solar atmosphere. Others come from lower regions. By observing the sun in different colours and wavelengths, scientists build a three-dimensional picture of its surface and atmosphere. The photosphere is visible to our eyes, but instruments can extend our vision, showing details that ordinary sight cannot separate. The sun becomes not just a bright disk, but a layered environment. The photosphere is sometimes the most overlooked part of the sun because it is the part we see every day. Familiarity has a way of making astonishing things seem plain. A person can live for decades under a star and rarely think about the layer where its light escapes. We notice the sun when it is too hot, too low in our eyes, absent behind clouds, or beautifully placed at sunset. But the visible face itself is always doing remarkable work. It is receiving energy from below, shaping it into escaping radiation, displaying convective patterns, revealing magnetic fields, carrying spectral signatures, vibrating with interior waves, and sending light outward across the solar system. It is not just a bright surface, it is the sun's main interface with the universe. And this interface is where the hidden and the visible meet. Below it, the interior is opaque, dense, and slow to release energy. Above it, the atmosphere becomes thinner, stranger, and in places unexpectedly hotter. At the photosphere, the sun changes from a trapped light environment to a free light environment. It is the threshold. Beneath, photons wander. Above, they stream. Beneath, energy is carried by radiation and convection through plasma. Above, light spreads into space, and charged particles move through magnetic structures. The photosphere sits between the sun we can infer and the sun we can see. That is why it matters so much. It is the layer that makes the sun visible, but it also hides the deeper layers behind its brilliance. It gives us daylight, but prevents us from seeing directly into the core. It looks smooth from Earth, but reveals granules, spots, and magnetic activity when observed carefully. It is familiar, but not simple. Every sunrise is the appearance of this layer over the horizon, though of course the sun itself is not rising in the old sense. Earth is turning, bringing your part of the world back into view of the photosphere's light. Morning is rotation, meeting starlight. As we continue outward from the photosphere, the sun becomes stranger in a different way. Above the visible face lies an atmosphere that is faint compared with the photosphere but full of structure. Magnetic fields rise from the surface into loops and arches. Energy can be stored and suddenly released. Sunspots mark active regions below, but flares and eruptions show what happens when magnetic tension above the surface becomes unstable. The photosphere is the bright face of the sun, but it is also the base of a more dramatic magnetic world, where dark spots, sudden flashes, and storms of charged particles reveal that our nearest star is not only shining, but constantly changing. The visible face of the sun may look smooth from Earth, but it is not a calm surface in the ordinary sense. It is the bright top of a moving plasma world, and threaded through that world are magnetic fields. These fields are not decorations, not gentle outlines drawn on the surface, but powerful structures that shape the behaviour of the sun's outer layers. They rise from below, twist through the photosphere, loop into the atmosphere, gather energy, and sometimes release it suddenly. When we talk about sunspots, flares, and magnetic storms, we are talking about the sun's restless magnetism becoming visible. The light is steady enough to give us days and seasons, but the star itself is not sitting quietly. It is turning, churning, tangling, and occasionally throwing a very large magnetic tantrum across space. To understand why this happens, it helps to remember what the sun is made of. It is not a solid ball, it is plasma, a hot mixture of charged particles. Because those particles carry electric charge, their motion is tied to magnetism. Moving charged particles can create magnetic fields, and magnetic fields can guide and restrain charged particles. In the sun, plasma and magnetism are woven together so tightly that one affects the other almost everywhere. When plasma flows, it can drag magnetic fields with it, When magnetic fields become strong, they can alter how plasma moves. The result is a star whose surface and atmosphere are shaped by invisible forces that behave a little like stretched rubber bands, a little like tangled thread, and a little like springs that have been wound too far and are waiting for a chance to snap back. The Sun rotates, but it does not rotate like Earth. Earth is mostly solid, so although its atmosphere and oceans move in complicated ways, the planet as a whole turns with a single basic rhythm. The Sun is plasma, so different parts can rotate at different speeds. Near the equator, the Sun completes a rotation faster than regions closer to the poles. This uneven rotation matters because it stretches and winds magnetic fields over time. Imagine drawing lines on a soft rubber ball, and then twisting the middle faster than the top and bottom. The lines would begin to shear and wrap around. The Sun does something similar with its magnetic field, though the real process is far more complicated and made of moving charged plasma rather than a rubber ball, which is fortunate because a rubber sun would raise several difficult questions. Beneath the photosphere, the convection zone is constantly stirring. Hot plasma rises, cooler plasma sinks, and enormous currents circulate through the outer interior. This motion helps generate and maintain the Sun's magnetic field through a dynamo process. The word dynamo here means that the movement of electrically conducting plasma creates magnetic fields. The Sun's magnetism is not simply left over from its formation like an old family heirloom sitting in a drawer. It is continually shaped by the Sun's own motion. Rotation stretches the field. Convection twists and churns it. Over time, magnetic energy builds in certain regions until it pushes up through the visible surface. When strong magnetic fields emerge through the photosphere, they can create sunspots. A sunspot is a region that looks dark compared with the surrounding surface because it is cooler. That does not mean it is cold. A sunspot by itself would still shine brilliantly against a dark sky. It only appears dark because the normal photosphere around it is so intensely bright. The strong magnetic field in a sunspot suppresses the upward flow of hot plasma from below. Since less heat reaches that patch of the surface, the region becomes cooler and therefore darker. It is rather like putting a heavy lid over a boiling pot in one small area, except the pot is the Sun, the boiling material is plasma, and the lid is magnetism. Sunspots often appear in pairs or groups. This happens because magnetic fields emerge from the Sun in loops. One part of a loop may rise out of the photosphere, curve through the atmosphere above, and return to the surface somewhere nearby. The two ends of the loop can appear as spots of opposite magnetic polarity, rather like the two ends of a magnet. Around these spots, the magnetic field is strong and complex. The central dark area of a sunspot is called the umbra, and around it is a lighter outer region called the penumbra. The penumbra often has a filament-like structure, showing how the plasma and magnetic field are arranged. Again, what appears from Earth as a little mark on the Sun can be larger than Earth itself. The Sun has a gift for making enormous things look like freckles. Sunspots are not permanent. They form, change, split, merge, and fade. Some last only a short time, others persist for weeks. Their numbers rise and fall in a cycle that takes about 11 years from one peak to the next. During times of low activity, the Sun may show very few spots. During active periods, many spots can appear, often in belts north and south of the solar equator. This cycle is tied to the Sun's magnetic field, which gradually becomes more tangled and active, then reorganizes and reverses. The Sun's magnetic north and south switch places as part of this cycle. It is a slow magnetic rhythm, not perfectly clock-like, but regular enough that scientists track it carefully. The activity cycle affects more than just the number of sunspots. When sunspots are numerous, the Sun is often more magnetically active in general. Active regions around sunspots can produce flares and eruptions. These events are not caused by fusion in the core suddenly surging, the core keeps working steadily. Flares and storms are outer magnetic events, driven by energy stored in twisted magnetic fields. This distinction is important. The Sun's deep nuclear engine is steady, while its magnetic surface and atmosphere can be stormy. It is a little like a person with a calm heartbeat but very dramatic hair in the wind. A solar flare is a sudden release of energy in the Sun's atmosphere. It happens when magnetic fields in an active region become unstable and reconnect. Magnetic reconnection is a process in which magnetic field lines rearrange themselves, releasing stored energy. Field lines are not physical strings, but they are a useful way to picture magnetic structure. When tangled magnetic fields snap into a new configuration, energy can be released rapidly, heating plasma and accelerating particles. The result can be a brilliant flash of radiation across many wavelengths, from radio waves to visible light to ultraviolet and X-rays. A flare is like a magnetic knot suddenly loosening and throwing energy into the surrounding plasma. Solar flares can be brief, lasting minutes to hours, but they can be extremely powerful. They occur in the Sun's outer atmosphere, especially above active regions where sunspots and complex magnetic fields are present. From Earth, we may not see a flare with ordinary eyes because the photosphere is already overwhelmingly bright, but instruments observing in ultraviolet or X-ray light can show flares dramatically. They appear as sudden brightenings, often near loops of magnetic field. The energy released can heat plasma to tremendous temperatures and send radiation across the solar system at the speed of light. This means the radiation from a flare reaches Earth in about the same time as ordinary sunlight. If a strong flare happens on the side of the Sun facing us, its electromagnetic effects can arrive very quickly. Flares can disturb Earth's upper atmosphere, especially the ionosphere, a region where solar radiation creates charged particles. Radio communications can be affected, particularly on the sunlit side of Earth. Navigation systems can experience disruptions. Satellites can be exposed to increased radiation. For most people on the ground, a flare may pass unnoticed, especially because Earth's atmosphere protects us from much of the harmful radiation. But for technology and for astronauts, solar activity matters. We live under a protective blanket of air and magnetic field, but our machines have wandered into places where the Sun's moods are more directly felt. Sometimes, active regions produce something even larger than a flare. The Sun can launch a coronal mass ejection, a huge eruption of plasma and magnetic field from the outer atmosphere. This is not simply light or radiation. It is material, charged particles embedded in magnetic structure thrown outward into space. A coronal mass ejection can contain billions of tons of plasma and can expand as it travels through the solar system. If it is directed toward Earth, it may arrive after a day or a few days, depending on its speed. Where a flare is like a sudden flash, a coronal mass ejection is like a great magnetic cloud hurled into space. One arrives as radiation almost immediately. The other travels as matter and field, slower but capable of shaking Earth's magnetic environment when it gets here. When such an eruption reaches Earth, it can trigger a geomagnetic storm. Earth has its own magnetic field, which forms a protective region around the planet called the magnetosphere. The solar wind, a continuous stream of charged particles from the Sun, is always interacting with this magnetic shield. Most of the time, the interaction is manageable and steady, but when a strong solar eruption arrives, it can compress and disturb the magnetosphere, injecting energy into near-Earth space. Charged particles can be guided down toward the polar regions, where they collide with atoms and molecules in the upper atmosphere. Those collisions produce auroras, the northern and southern lights. Auroras are among the most beautiful visible effects of solar magnetism. Curtains of green, red, purple and white light can ripple across polar skies, moving slowly or suddenly, glowing like the atmosphere has learned to breathe in colour. The light comes from oxygen and nitrogen in the upper atmosphere being excited by incoming particles and then releasing energy. The colours depend on the type of atom or molecule, the altitude, and the energy involved. Although auroras may seem serene from the ground, they are the visible edge of a magnetic storm. They are Earth's atmosphere responding to particles from the sun. A quiet polar night can become a screen for solar activity that began with tangled magnetic fields on a star 150 million kilometers away. Geomagnetic storms can also affect technology. Strong storms can induce electrical currents in long conductors on Earth, such as power lines and pipelines. They can disturb satellites, alter their orbits slightly by heating and expanding the upper atmosphere, interfere with radio signals and affect navigation systems. Airlines on polar routes may adjust paths during intense solar events because communication and radiation conditions can change. Astronauts outside Earth's atmosphere are especially vulnerable because they do not have the same protection as people on the ground. This is why space weather forecasting is an important field. Just as meteorologists watch clouds, pressure systems and storms in Earth's atmosphere, space weather scientists watch the sun's active regions, flares, solar wind and eruptions. The phrase space weather may sound like something invented to make forecast even more complicated, but it is very real. Earth is surrounded by a space environment shaped mainly by the sun. The solar wind flows past us all the time. The sun's magnetic field extends outward through the solar system. Solar storms can change conditions around Earth. For modern civilization, with satellites, electrical grids, communications, aviation, and future plans for deeper space travel, understanding space weather is not optional. The sun is not just a distant light source, it is an active neighbour whose magnetic behaviour can reach our technology. Still, it is worth keeping the scale of risk in perspective. Most solar activity is handled very well by Earth's atmosphere and magnetic field. For someone lying in bed listening to this, a solar flare is not something to worry about in the ordinary sense. It will not come through the window and steal the blankets. The danger is mostly to technology and to people in space or high-altitude polar routes during strong events. Earth has lived with solar storms for billions of years. Life evolved under this star, with its cycles and outbursts. Our concern today is partly because we have built systems that are sensitive to disturbances in ways trees and rocks are not. A forest does not need global positioning satellites. A mossy stone is rarely troubled by radio blackout. Sunspots and flares also teach us that the sun has weather of its own, though it is not weather like Earth's. There are no rain clouds, no snow, no gentle drizzle tapping on solar windows. Solar weather is magnetic and plasma-based. It includes flowing charged particles, eruptions, radiation bursts, waves, shocks, and magnetic structures. It is controlled by forces that become important when matter is electrically charged and moving at stellar temperatures. The sun's weather is not driven by water vapor and air pressure in the way ours is. It is driven by magnetized plasma. And because the sun rotates and its magnetic fields evolve, this weather changes across time. The solar wind is part of this larger picture. Even when the sun is not producing a dramatic eruption, it constantly releases a stream of charged particles into space. This wind flows outward from the sun's outer atmosphere and fills the solar system. It carries the sun's magnetic field with it, forming a vast influence that reaches far beyond the planets. Earth moves through this solar wind as it orbits the sun. Our magnetosphere deflects much of it, creating a long tail away from the sun, a bit like a windsock shaped by invisible particles. Without Earth's magnetic field and atmosphere, the solar wind would interact far more directly with the surface, as it does with some other worlds. The solar wind also helps shape the boundary of the sun's domain. Far beyond the planets, the solar wind eventually slows and meets the material between the stars. The bubble carved out by the solar wind is called the heliosphere. Earth and the other planets orbit inside this bubble. In a real sense, we live inside the extended atmosphere of the sun. The visible sun is only the bright central object. Its influence reaches outward through particles and magnetic fields, enclosing the solar system in a vast region shaped by our star. That is a remarkable thought. The sun is not limited to the disk we see. It fills space around us with a subtle but continuous presence. Sunspots are useful markers for studying solar rotation and magnetic activity. Because they move across the visible disk as the sun turns, early observers could use them to determine that the sun rotates. But they also noticed that spots appear more often at certain latitudes and that their positions shift during the solar cycle. At the beginning of a cycle, sunspots often appear at higher solar latitudes. As the cycle progresses, new spots appear closer to the equator. When plotted over time, their pattern forms a shape sometimes compared to butterfly wings. It is a lovely image for a technical graph, and it shows that the sun's magnetism has organized long-term behavior beneath its apparent complexity. Even the chaos has habits. The sun's magnetic cycle is not perfectly regular. Some cycles are stronger than others. Some have many sunspots and energetic activity. Others are quieter. In the past, there have been extended periods with very few sunspots, suggesting that the solar dynamo can change its behavior over longer timescales. Scientists study these variations using telescopic records and indirect evidence from Earth, such as changes in certain isotopes affected by cosmic rays and solar activity. The sun is stable in its core output, but its magnetic activity has moods across decades and centuries. It is not random, but it is not a clockwork toy either. Active regions on the sun often begin when magnetic flux rises from below the photosphere. As it emerges, it disrupts convection and creates spots. Above the surface, loops of plasma trace the magnetic field. These loops can glow brightly in ultraviolet and X-ray observations, revealing the structure of the corona. Some loops are stable for a time, arching gracefully above sunspots. Others become twisted or stressed. If conditions change suddenly, reconnection can occur and energy can be released. The sun's atmosphere is full of these magnetic architectures, rising from the visible face into the faint outer layers. They are invisible to ordinary sight unless observed in special wavelengths, but they are central to solar activity. The corona, the sun's outer atmosphere, is much hotter than the photosphere, which is one of the long-standing puzzles in solar physics. Magnetic fields and waves are thought to play major roles in heating it. This means the same magnetic complexity that creates sunspots and flares may also help explain why the outer atmosphere reaches such high temperatures. The photosphere is the bright visible face, but above it the corona forms a delicate high-temperature plasma environment. During total solar eclipses, when the photosphere is blocked, the corona appears as a pale glowing halo. It looks soft and elegant, but it is magnetically structured and dynamically active. Again, the sun specializes in looking calm from a distance while being physically intense up close. A flare or eruption does not happen in isolation from the rest of the sun. It is the result of energy that has been stored in magnetic fields, often built up by motions at and below the surface. Plasma flows shuffle the footpoints of magnetic loops. Rotation and convection twist the fields. New magnetic regions emerge. Opposite magnetic structures press together. The system becomes stressed. Then, when reconnection occurs, energy is released. This chain of events can be difficult to predict precisely because the magnetic field is complex and three-dimensional. Scientists observe active regions carefully, looking for signs of instability, but the sun remains a challenging forecaster. It is a reminder that even our nearest star, watched constantly by instruments, still has secrets in its motion. Some solar eruptions are accompanied by shock waves that travel through the corona and solar wind. These shocks can accelerate particles to high energies. Solar energetic particles can reach Earth quickly and pose radiation hazards to spacecraft and astronauts. They can also affect instruments and electronics in space. Understanding these particle events is especially important for future missions to the Moon and Mars, where astronauts would be outside much of Earth's protective magnetic shield. The sun is both the source of energy that makes life possible and a radiation environment that space travelers must respect. It is friendly from the right distance and behind the right protections. Up close, it is less of a kindly lamp and more of a nuclear plasma star with boundaries. The largest solar storms known from history show how strongly the sun can affect Earth. In the 19th century, a powerful geomagnetic storm produced auroras visible far from the poles and disturbed telegraph systems. If a similar event occurred today, it could stress modern electrical and communication networks. This does not mean catastrophe is inevitable, but it does mean preparation matters. Scientists monitor the sun using spacecraft that observe its surface, atmosphere, magnetic fields, and particles. Space weather centers issue alerts when strong flares or eruptions are detected. Our civilization now keeps watch on the sun not only because it is beautiful, but because our infrastructure is spread into space and tied together by delicate timing and signals. There is a strange intimacy in this. The same star that helps grow wheat and warm oceans can also disturb satellites and power grids. The same magnetic fields that make auroras can complicate radio communication. The same active regions that appear as dark spots on the photosphere can launch storms into interplanetary space. The sun is not good or bad in this. It is a star behaving like a star. We are the ones who must learn its patterns, build protections, and understand the environment we inhabit. Living near a star means receiving both its steady light and its occasional weather. Sunspots also remind us that darkness can be informative. Those dark patches are not absences of solar activity, but signs of concentrated magnetic field. They are windows into the sun's dynamo. A spotless sun can mean a quieter part of the cycle. A spot-covered sun can signal heightened magnetic activity. Observing spots over days reveals rotation. Observing them over years reveals cycles. Observing their structure reveals how magnetic fields shape plasma. Something that once looked like a blemish is now a key diagnostic tool. Science often works this way. A feature that seems like an imperfection becomes evidence. Flares remind us that stored energy can be released suddenly. The sun's magnetic fields can build tension over time, then reorganize in minutes. This is different from the slow energy flow from the core. It is more local, more abrupt, and more variable. The photosphere and corona are where the sun's steady power becomes complicated by magnetism. The core is the long, quiet engine. The magnetic atmosphere is the restless outer weather. Both belong to the same star, but they operate on very different timescales. One supports billions of years of light. The other can change a region of the sun in moments. Magnetic storms remind us that the sun and Earth are connected across empty space. Space is not truly empty in the simple sense. It contains fields, particles, radiation, and the solar wind. Earth's magnetic field stands in that flow, sometimes calm, sometimes disturbed. Auroras are the visible sign of connection. Technological disruptions are the practical sign. The solar system is not a collection of isolated objects floating in nothing. It is an environment shaped by the sun, with planets moving through the star's extended influence. Even so, the sun's magnetic storms are only part of its story. They are dramatic and important, but they ride on top of a deeper stability. The sun can produce spots, flares, and eruptions because it is a magnetized plasma star, but it keeps shining because fusion continues in the core, and the whole structure remains balanced against gravity. The storms do not mean the sun is unstable in the everyday sense. They mean its outer layers are active. Beneath the drama, the fundamental engine remains steady. That combination is what makes the sun so fascinating. It can be reliable and restless at the same time. It can give Earth a stable supply of light while also sending magnetic storms through space. It can appear serene in the sky while its surface writhes with plasma, and its atmosphere flashes with stored energy released. As we move from the sun storms back toward the larger question of its lifetime, it becomes clear that the sun is held together by more than one kind of balance. Its magnetic fields twist and erupt near the surface. Its convection zone boils beneath the visible face. Its radiative interior delays and smooths energy. its core fuses hydrogen steadily under immense pressure. Every layer has its own kind of motion, its own pace, its own role in the life of the star. The sun keeps shining not because it is simple, but because these processes fit together in a long-lasting structure, and that structure has a past, a present, and a future that will eventually change the entire solar system. For all its storms and restless surface motion, the sun keeps shining because its deeper structure is remarkably well balanced. Beneath the sunspots, beneath the flares, beneath the boiling convection, and the long wandering paths of photons, there is a simple physical arrangement holding the whole star together. Gravity pulls inward, heat and pressure push outward. Nuclear fusion in the core supplies the energy that keeps that pressure strong. As long as the core has enough hydrogen to fuse, and as long as the sun can maintain that balance, it continues to shine with the steady brightness that has shaped Earth for billions of years. It is not a flame trying not to go out. It is not a battery draining in the usual sense. It is a star in a long stable phase of life, held open by the energy made at its centre. This balance has a name in physics, but the idea matters more than the label. Imagine the entire weight of the sun pressing down on the core. Every layer of plasma pulls inward because of gravity. If nothing resisted that pull, the sun would collapse, becoming smaller and hotter as it fell inward. But the core is hot because fusion is happening there. Heat means particles are moving rapidly, colliding, pushing, and creating pressure. Radiation also contributes to the outward support. Together, this pressure resists gravity. The sun is not rigid. It does not have beams or walls. It supports itself through motion and energy. The whole star is like a held balance between collapse and expansion, and it has remained in that balance for a very long time. The balance is self-correcting. If the core cools slightly and fusion slows, gravity gains a small advantage. The core contracts a little, and contraction raises the temperature and pressure. That makes fusion more likely again. If fusion becomes a little stronger and produces extra heat, the core expands slightly. Expansion cools it and reduces the fusion rate. In this way, the sun naturally regulates itself. Not with intention, not with a control room, not with a tiny solar technician adjusting knobs while wearing protective goggles, but through the built-in response of matter under gravity. This feedback keeps the sun from wildly flickering or exploding outward. It is one of the reasons the sun can seem so reliable from Earth. This reliability is not absolute stillness. The sun changes in many ways. Its surface activity rises and falls with the magnetic cycle. Sunspots appear and fade, flares erupt, the solar wind varies. But the deep energy production in the core changes very slowly. The core is the slowest part of the story. It does not care about our seasons, our calendars, or whether Monday has arrived with unnecessary confidence. It works on stellar time, steadily transforming hydrogen into helium, releasing energy and holding the star in its long middle life. The sun we know is possible because this central engine is stable. The sun is currently in what astronomers call the main part of a star's life, when hydrogen fusion in the core is the main power source. This stage lasts for billions of years for a star like the sun. More massive stars live shorter lives because their cores are hotter and their fusion proceeds much faster. They shine brilliantly and spend their fuel quickly. Smaller stars can live far longer, glowing dimly and conserving their hydrogen with extraordinary patience. The sun is somewhere in the middle. It is bright enough to warm Earth, but not so massive that it rushes through its fuel. That middle nature is part of why life had time to develop here. A star that lived only a few million years would not have offered Earth enough time for oceans, cells, forests, animals, and eventually someone wondering sleepily what happens inside the sun. The sun formed about 4.5 billion years ago from a collapsing cloud of gas and dust. Most of the material gathered into the young star. The leftover material flattened into a disk around it, where planets and smaller bodies formed. In the early days, the young sun was more active in some ways, with stronger outflows and a more turbulent environment. Over time, it settled into its stable hydrogen fusing phase. Since then, it has been slowly changing. Slowly is the key word. The Sun has not been exactly the same throughout Earth's history. It was dimmer when Earth was young. Its brightness has gradually increased as the core has evolved. This increase is not dramatic on human timescales, but across billions of years it matters greatly. The reason for the gradual brightening lies in the core. As hydrogen fuses into helium, helium builds up in the central region. Helium behaves differently from hydrogen under these conditions. The core adjusts, becoming denser and hotter over time, and the fusion rate slowly increases. This makes the Sun shine a little more brightly as it ages. The change is gentle by the standards of stars, but Earth is sensitive to the amount of sunlight it receives. Long before the Sun reaches the end of its life, its increasing brightness will become a serious problem for our planet. This is an uncomfortable but important part of the Sun's future. The Sun will not suddenly fail tomorrow. It will not explode next week. It is not close to dying in any practical human sense. But over very long timescales, as it brightens, Earth will receive more solar energy. This will affect climate in ways that become increasingly severe. Oceans may evaporate more rapidly. Weathering processes and atmospheric chemistry will change. The conditions that make Earth comfortable for complex life will not last forever. The Sun has been a generous source of stability, but that stability is not permanent. Habitability is a temporary arrangement, even when temporary means billions of years. It may seem strange that the Sun's future can be both very far away and deeply important. Human minds are not naturally built for billions of years. We are good at thinking about breakfast, birthdays, deadlines, and whether a package has actually been delivered or is simply enjoying a private holiday somewhere in a warehouse. Stellar time is different. The Sun's evolution is slow enough that it feels almost frozen from our perspective, yet physics is always moving it forward. Hydrogen is being used, helium is accumulating, the balance is changing, the Sun is stable, but it is not static. Eventually, the hydrogen in the core will become too depleted for the Sun to continue its current kind of fusion there. When that happens, the structure of the star will change. The core, now rich in helium, will no longer produce enough energy through hydrogen fusion in the center. Gravity will begin to compress it. As the core contracts and heats, hydrogen fusion will continue in a shell around the core, where enough hydrogen remains. This shell burning will produce energy at a higher rate, and the outer layers of the Sun will expand. The Sun will leave its long stable phase and become a red giant. A red giant is not just a slightly larger Sun with a warmer colour. It is a major transformation. The outer layers expand enormously, becoming cooler at the surface but much more luminous overall because the star becomes so large. The Sun's colour will shift toward redder tones as its surface temperature drops, even while its total energy output increases. It will swell outward, changing the solar system. Mercury will be engulfed. Venus is very likely to be engulfed as well. Earth's fate is more complicated in detail, because the Sun will lose mass and planetary orbits will change, but Earth will certainly no longer be the mild blue world we know. Even if it avoided being swallowed directly, its surface would be scorched beyond recognition. Oceans would be gone. The familiar planet would become a memory written only in geology, if anything remained to read it. This may sound dramatic, and it is, but it is not a near-future event. It lies billions of years ahead. The purpose of saying it is not to create worry, but perspective. Stars have life cycles. The Sun is not an eternal fixture. It is an evolving object, and Earth's current comfort depends on meeting the Sun at the right time in its story. We live during the Sun's long, steady middle age, when its light is strong enough but not too strong, stable enough for life to flourish, and calm enough overall that planets can keep their climates within workable bounds. We are living in a fortunate interval. Inside the future red giant Sun, the helium core will keep contracting and heating until helium fusion can begin. At that stage, helium nuclei can combine to form heavier elements such as carbon and oxygen. This will not happen now because the current core is not hot enough for helium fusion, but after the core contracts in the red giant phase, conditions will eventually reach the necessary level. When helium fusion begins, the Sun will settle into a new, shorter phase of stability. It will no longer be the Sun we know, but it will still be a star finding a new balance between gravity and nuclear energy. The Sun is not massive enough to fuse elements much heavier than carbon and oxygen in a sustained way. Larger stars can go through a sequence of fusion stages, building heavier and heavier elements in their cores, until they reach a crisis that can end in a supernova. Our Sun will not do that. It is too modest in mass for such a violent ending. There is something almost reassuring about this. The Sun is powerful beyond human comparison, but among stars it is not the kind that ends by tearing itself apart in a colossal explosion. It will not become a supernova. It will take a quieter path, though quiet is again a relative word when the outer layers of a star are being shed into space. After its red giant stages, the Sun will become unstable in its outer layers. It will pulse, lose mass, and cast off shells of gas into space. The exposed core left behind will be extremely hot, and its radiation will light up the expelled material. This glowing cloud is called a planetary nebula, though the name is misleading. It has nothing to do with planets except that early observers saw some of these objects through small telescopes and thought they looked a bit like planetary disks. A planetary nebula is the beautiful, brief aftermath of a star like the Sun shedding its outer layers. The gas expands outward, enriched with material processed during the star's life. For a while it glows in delicate shapes, often sculpted by winds, magnetic fields, and the geometry of the ejection. At the centre of that nebula will be the Sun's remnant core, a white dwarf. A white dwarf is not a star powered by ongoing fusion in the ordinary sense. It is the hot, dense, leftover core of a dead star, supported by quantum effects rather than by heat from active fusion. It will be about the size of Earth but contain a large fraction of the Sun's remaining mass. This makes it incredibly dense. A spoonful of white dwarf material, if one could somehow scoop it up without causing a physics and engineering scandal, would have enormous mass. The white dwarf will glow because it is hot, gradually cooling over immense stretches of time. It will not have a new source of energy to keep it shining forever. It will simply radiate away its stored heat, fading slowly into darkness over times longer than the current age of the universe. This is the Sun's distant future. A main sequence star now, a red giant later, a shedding of outer layers, a planetary nebula, and finally a white dwarf cooling in the dark. It is a complete life story, but one that unfolds so slowly that human history occupies only the smallest blink within it. The Sun has already existed for billions of years, and will continue in its current stable state for billions more. Its later transformations are real but remote. For us, the Sun remains the same dependable star we know, rising because Earth turns, shining because the core fuses hydrogen, and warming our world because we orbit at a distance where sunlight can sustain liquid water. The fact that the Sun keeps shining also depends on its mass being just right for this life path. If it had been much less massive, it would have been dimmer and cooler, perhaps a red dwarf, living for far longer but providing a different environment for planets. If it had been much more massive, it would have burned hotter, brighter and shorter, possibly ending in a supernova after a brief life by cosmic standards. The Sun's mass determines its core temperature, fusion rate, brightness, lifetime and fate. In stars, mass is destiny to a remarkable degree. The Sun's particular mass gave it a long, stable life, enough brightness for Earth, and a future that ends not in explosion but in gradual shedding and cooling. There is another question hidden here. Why does the Sun not simply run out of energy quickly, given how much it radiates every second? The answer is that nuclear fusion is extraordinarily efficient compared with chemical energy, and the Sun is enormous, Only the core is actively fusing hydrogen at the needed rate, but that core contains a vast amount of fuel. The sun also releases energy in a controlled way, regulated by pressure and gravity. It is not spending its energy recklessly. It is releasing it through the slow process permitted by its internal conditions. That combination of abundant fuel and regulated fusion allows the sun to shine for billions of years. The sun also keeps shining because energy transport through the star smooths its output. The energy made in the core does not instantly reach the surface. It passes through the radiative zone and convection zone, delayed and redistributed. This means the surface brightness is not a direct moment-by-moment reflection of every tiny change in the core. The star has enormous thermal inertia. It is slow to change because it contains so much hot material and because energy takes time to move through it. This slow response helps make it stable. The sun is not a light bulb that reacts instantly to a switch. It is a vast plasma body with deep reserves and long internal timescales. From Earth, this steadiness has shaped almost everything. The length of the day comes from Earth's rotation, but the meaning of day comes from sunlight. The year comes from Earth's orbit, but the seasons come from the changing angle of sunlight and the tilt of our planet. Climate depends on the balance between incoming solar energy and outgoing heat. Plants use sunlight to make chemical energy. Animals depend on plants directly or indirectly. Human cultures built calendars around the sun's motion in the sky. Ancient monuments tracked solstices. Farmers watched the seasons. Sailors and travellers used solar direction. Even now, with atomic clocks and satellites, our daily language remains full of sunrise, sunset, noon, morning, evening and daylight. The sun is not only a physical object, it is built into how life organises itself. And still, the sun is just one star. This is not meant to make it seem less special, but to place it properly. Across the galaxy, stars are being born, shining, aging and dying. Some are younger than the sun, some are older, some have planets, some have already become white dwarfs, some will end as neutron stars or black holes. The sun is our local example of a process happening everywhere in the universe. By understanding why it keeps shining, we understand something about the life of stars in general. The warmth on your skin is connected to the same physics that lights distant points in the night sky. There is a quiet clarity in the sun's story. It formed from a cloud. Gravity compressed it. Fusion began. For billions of years, hydrogen fusion has held it in balance. Its energy has crossed the solar system and shaped Earth. Its magnetic fields have produced storms and auroras. Its surface has glowed steadily enough for life to grow beneath it. In the future, its core will change. Its outer layers will swell, and it will become a red giant. Later, it will shed those layers and leave behind a white dwarf. None of this requires purpose. None of it is arranged for us. It is matter obeying physics. And yet, from those impersonal processes comes the personal world of mornings, shadows, gardens, weather, and the warmth of a room in a late afternoon. So when we ask why the sun keeps shining, the answer is both simple and layered. It shines because gravity made its core hot and dense enough for fusion. It keeps shining because fusion produces the pressure that balances gravity. It remains steady because the core regulates itself and the interior transports energy slowly. It will not shine this way forever because hydrogen in the core is gradually being used and the star must eventually adjust. The sun is stable because it is changing slowly, not because it is unchanging. That may be one of the most useful truths about it. Stability in nature is often not stillness. It is a managed motion, a balance maintained through continuous activity. Right now, as you listen, the sun is doing all of this, whether it is above your horizon or on the other side of the world. Its core is fusing hydrogen. Its radiative interior is delaying energy. Its convection zone is boiling upward. Its photosphere is releasing light. Its magnetic fields are twisting and relaxing. Its solar wind is flowing outward past the planets. Somewhere on Earth, morning is arriving, Somewhere else, evening has settled in. Somewhere, sunlight is touching leaves, warming stone, flashing on waves, or waiting just below the horizon for Earth to turn a little farther. And perhaps that is a good place to leave the sun for now, not as a simple ball of fire but as a working star. A star with a hidden core, a long interior journey for light, a boiling outer layer, a visible face, magnetic storms, and a future written slowly by fusion and gravity. The sun is familiar because we live with it every day, but it's not ordinary in the small sense. It is ordinary only in the cosmic sense, one star among many doing what stars do. From our small planet, that ordinary stellar work becomes everything. Daylight, weather, food, time, warmth, the conditions for life. So the next time sunlight reaches your window, you might think of the long story behind it, not in a hurried way, and not as something you need to hold on to tightly. Just for a moment you can remember that the light began in the deep core of a star, wandered through plasma, rose through boiling layers, escaped from the photosphere, crossed space, passed through the air, and arrived quietly in your room. It is a very long journey for something that feels so immediate. And if your eyes are growing heavy now, that is perfectly all right. The sun will continue its work while you rest, shining through the long balance of gravity and fusion, keeping its steady place at the center of our days, ready to meet the morning whenever your part of Earth turns toward it again.